me ouvindo por aí? Beleza.
Olá, Teloli, tudo bem?
Olá, Samuel, tudo bom?
Tudo bem. Deixa eu tentar abrir aqui, que justo hoje o meu computador deu de travando, cara.
Hum,
Esse Google Meet, cara, esses sistemas da Google, não sei se você sabia, eles ocupam muita memória RAM. Muita.
sim.
E, e fica muito complicado sempre. O Zoom, ele é muito melhor, cara. Ele é
Tem
bem mais leve.
tem limitação de tempo, talvez?
O Zoom tem limitação de tempo, mas o Google Meet também tem. Ele não tem essa limitação de tempo porque a gente usa uma versão que é... A Unesp usa uma versão que é paga, né?
Ah,
Mas, se não, também era igual o uso do Zoom, né? Mas o Zoom, quem tem a licença, é muito melhor, assim. A imagem do Zoom é muito melhor.
uhum.
E, muitas vezes, o problema que a gente tem de conexão é um problema associado a ele. Ah, consegui abrir. Consegui abrir o PDF da Informações de Defesa.
Eu vou desligar aqui a internet do celular para ficar concentrado.
E hoje o dia está corrido ainda, que eu tenho que ir para Rio Preto ainda hoje. E eu ainda tenho que pegar os documentos da tese. Eu pedi para a Márcia me mandar, porque eu comentei de a gente fazer esses documentos todos, até os modelos em inglês feito.
Ah, tá. Sim, sim.
Bonjour Gaël, ça va?
Salut.
Salut Samuel, ça va?
Salut. Ça va bien.
Bon,
Ça va bien.
je vais essayer de remettre la vidéo. Hop
Oui,
là.
c'est...
J'ai mis un t-shirt brésilien.
Mais
Oui,
c'est
c'est...
cool, hein?
euh,
C'est cool.
Au Brésil ici, c'est complètement, c'est un grand froid au
C'est
Brésil
vrai?
maintenant. Il a sauté
L'hiver
à
froid.
5 degrés.
Non.
5 degrés.
La même chose ici,
5
à
degrés pour
Tupã.
nous, c'est impossible de supporter parce que, par exemple, dans ma maison, il n'a pas de système de chauffage. Alors,
D'accord.
si je mets la main au, au wall, c'est complètement froid.
Ouais.
D'accord.
Ici à Besançon, je pense que la température est agréable. Il y a
Surtout
un
que là,
canicule.
là, je suis au sud de la France, je suis en Corse, alors tu vois.
Ah,
Surtout
d'accord,
sur
c'est
la
mieux.
Corse. Corse, oui, c'est pas mal, hein.
D'accord, c'est mieux, c'est mieux.
Ouais.
Mais
Bon,
il y a quelle canicule en France cette année?
non, cette année, c'est température vraiment normale. On est
Normal.
à 20, 28 degrés, il y a eu
D'accord.
pas mal de pluie.
Je me rappelle en 2019, quand j'étais à Paris, en juillet,
Mm.
il y était un canicule très fort. Mais je rappelle, il y a la sens thermique de quelques
Mm.
places à Paris de presque 50 degrés. C'est
Mm.
complètement fou de supporter.
Ouais, il y a eu ça en 2019 et 2020. Mais là,
Et
cette année c'est mieux. C'est plus agréable, hein, franchement.
c'était encore pire que Brésil, je pense. Parce que, alors, 50 degrés,
Oui,
c'était pas très.
oui. C'est pas courant, par exemple. Il y a beaucoup de villages au sud du Brésil. Je pense que presque 40 villages il y a de la neige. Pour nous, c'est incroyable d'avoir. Normalement, il y a un ou deux places, surtout sur la montagne, au sud du Brésil, qu'il y a de la neige. Mais grand village, comme ça s'appelle là, Gramado, Canela, qu'il y avait beaucoup de neige, qui ça permet, par exemple, de faire un...
Du ski?
Non, c'est pas du ski.
Non,
C'est
pas du ski.
Des raquettes?
Comme dit. Oui, pour faire des raquettes, pour faire
Des bonhommes de neige?
des bonhommes de neige. Oui.
Ouais.
C'est une chose incroyable.
Ouais. Non, mais là c'est bien.
Oi, João.
Bom dia, Samuel. Bom dia, tudo
Tudo
bom?
bem?
Bom dia.
Olá, professor, tudo bem?
Alô.
João Antônio, I'd like to meet you, Gael, Professor Gael Chevalier, from
Hi.
Besançon.
Hi. Yeah.
He was the supervisor of Rafael during his sandwich Besançon.
Okay.
Gael,
I'm pleased to meet you.
okay. We are waiting, stopping the pandemic, to try to rearrange a visit of Gael in Ilha Solteira. Maybe next week.
Wow.
Maybe next year.
Next
Okay.
year, yeah.
Next year.
Here
Probably.
You are welcome to Ilha Solteira.
Here in France the COVID is very quiet now. It's almost finished, I think. There is some clusters, but very small, and
I think
the situation is really good in hospitals. So I think it's almost finished.
for us it started to decrease the name of cases now, but I think the situation would be better in September and October, because the most part of the population has the 2 doses of the vaccine. Complete immunization of the people. Rafael,
Okay,
are you take the vaccine?
Not yet. I will take
You
the
are
next
very
week.
young.
Yes.
Yeah.
26. It's but yes.
Yeah, but
You are right.
I think the main problem is the new variant of
Variation.
the virus.
Yeah.
This is making very confusing the how to deal with the situation.
Yes, that's true.
Even in most of the São Paulo state, my children, they are 16. It's supposed to have the vaccine in next month, almost. But this new variation, it's quite complicated.
Yes, it's true. That's true. The complicate in Brazil. I don't know what's happening in France, Gael, but in Brazil, there's a lot of
it's the
politicians.
same.
There's
Yeah,
a lot
it's
of
the same, but it depends on the vaccine you use. For the guys who use the Pfizer, it seems that it's not so bad. We got 4, I don't remember, 3 or 4 vaccines, but we got the AstraZeneca, and with the AstraZeneca, it seems that it's worse than with the Pfizer, with the new variant of the virus.
The biggest problem is that we need to have a large amount of the people completely immunization. The problem in Brazil that is the politicians, they want to open the economy, to open the commerce, the economy, the things like this, before you have an amount of the people completely immunization. For example, in São Paulo, the governor of São Paulo, decided to open all the economy next month. But there's not the time to have a complete immunization. For example, the young people start only to the first dose. The first dose, but it's not complete immunization. Mainly in Brazil, that we use two types of vaccine, mainly AstraZeneca and CoronaVac from China with Brazil, Butantan Institute. And we have the Pfizer, we have Janssen, but not with a large number. And another problem in Brazil that happened, in my point of view. Hello, Daniel. So, Daniel, I would like to meet Rafael, or my PhD
Candidate.
student. Yes, the candidate.
Hello, Professor.
Professor Gaël Chevalier from University de Franche-Comté, Bourgogne-Franche-Comté in France. That was the supervisor of Rafael during the sandwich. Daniel Castelo from Federal University of Rio de Janeiro.
Nice to meet you.
Nice to meet you. João Antônio Pereira from UNESP.
Bom dia, Daniel.
Bom dia.
Now we're talking about the vaccine in Brazil, COVID, and about the weather. What's the weather in Rio de Janeiro?
I'm not in Rio. I am in Salvador.
It's better.
Okay.
Yeah. Well, here is tropical weather mostly all along the year.
Yeah.
So all these days have been 20 and something, 25 or something.
Salvador, we are in vacancy in Salvador?
No, we have a newborn.
Oh.
That is 2 months old.
Congratulations.
So,
Congratulations.
And thank you. And as I was in home office, we decided that it would be better for us to have our baby here, because the family of my wife all of them are from Salvador.
Salvador, I love this city.
Nice.
That's very good, very fantastic.
Yes, next year in my vacancy, I decided to visit again Salvador.
Yeah.
Because this year I'm not in vacancy. I not travel for vacancy because the pandemic. I think the first in Brazil, I decide to visit again Salvador.
Yeah, and I think that if you have been to Salvador, probably you have been to Praia do Forte.
Okay.
Yeah, that is very, very nice.
But in Salvador, I like it to stay in Porto da Barra, in the Barra.
Okay.
Hi, Professor Garoto.
Hello.
Hi, good morning.
Hello,
So
good morning.
I'd like to meet the people. Rafael, I think that you meet again. Rafael, Professor Gaël Chevalier from Université de Franche-Comté, Bourgogne-Franche-Comté, that you meeting during a member during that last year of my student.
Nice to meet you again, Professor Chevalier.
Yeah.
João Antônio, I think it's an old friend. E Professor Daniel Castelo from Federal University of Rio de Janeiro, but he is now in Salvador. I think the best weather for now it's Daniel Castelo and Gaël Chevalier, because Gaël, we are in south of France, the sud of France.
Yeah, it's the best season in France, especially in the south.
Yes. Are you using Havaianas again? Because your t-shirt is the Brazil.
I get it.
Yeah.
Because of the defense.
Good.
We are waiting professional break. I think in São Carlos was the worst weather now.
Yes, 3 hours ago, about 6:30 in the morning, or a little less than that, we have reached 1 degree Celsius with wind chill, where we're feeling something like 0 degrees Celsius.
Yes, I think it's definitely you win.
Yeah. I don't know what kind of a winner I am right now, but well, I'm from São Carlos, so it's it's a pleasant weather, but this winter has been very tough. Anyway, I'm sorry for the background noise. I'm gonna turn off my microphone in a few minutes because I came to the university this morning in order to have a better connection with the internet. But they're cutting out some trees outside, and maybe you can listen to the saw on the background. But Rafael, I
Don't worry,
will not disturb you much longer. So
no, don't worry,
I'm
Professor.
sorry if you're listening to this terrible noise. I am. So no problem. Hello, João Antonio. How are you this morning?
Fine, and you?
Good. Nice to see you again.
Me too.
Wonderful. Daniel, it's been a long time since I saw you last time. I think it's I don't know how many years. How are you doing? I think your microphone is off.
Microphone is off.
Oh, thank you. Yes, it's been a long time. Maybe I last saw you 8 years ago, perhaps in some Dynami.
Yes.
Yes. But we are good. Thank you. What about you?
Yes, fine. Also, as well, I left the the position of a dean of the school a couple of years ago, and I'm retired back to my academic duties. I have a few years until I have time to retire, but I'm not thinking about retiring right now. I'm just thinking about enjoying these years and trying to have some work done. And
yeah, that's good idea. That's very good idea.
Couple of personal projects like graduate books for structural dynamics students, and of course interact with my friends in research projects. But it's a long way when you dedicate most of your academic career to the administration like I did. But I think I'm going back to the academics right now, and who knows, I might have some good stuff to share with you guys in the near future. Looking forward to meeting you in person again soon.
Yes. Thank you. I'm looking forward for you to see you again soon.
Yes.
Perhaps in some next year we have conferences and you have this opportunity.
Of course.
That will be very nice. Well, what's the temperature now in São Carlos?
Right now, let me see on my cell phone. It's really cold here, it's about 5 degrees Celsius.
5 degrees Celsius, yes.
Yeah, it's 9:06 in the morning, and today is supposed to be the coldest day in the year so far.
Okay.
Yeah, in the first hours of the morning, we have reached something like 0. By 3 or 4 o'clock in the morning, it was like a 0 degrees centigrade and Celsius, and with the wind chill, the feeling of about -2. So it was a freezing temperature in São Carlos.
Yeah, freezing temperature, yes.
Yeah.
Really
think, Samuel, I think we can manage to organize a business between France and Brazil to send winter clothes, because we have a lot of winter clothes here in France. So
Yeah.
and with the climate change, I think we can send to you our winter clothes.
Wonderful.
Yes.
I'm also considering to rent like one of those houses made of wood, like we have in the United States, because the heating is better for winter purposes. It's terrible in the summer, but we have air conditioning in the summer, or we're going to have air conditioning in the summer as long as we have electric power this coming summer, because things in Brazil are getting a little bit cumbersome as far as electric power consumption is concerned, but we never know. Yeah. I have a son that lives in France right now. He's in Grenoble.
Okay.
He's a student. He's just graduated from, or he's going to be graduating from the Polytech on material science engineering.
Oh yeah, I remember you already explained.
Yeah, and he's getting involved in a doctorate degree financed by Schneider. He's working for Schneider right now, and he's going to be doing some copper interactions stuff or material science design project with Schneider. for the next 3 years. So
Okay. But will he do his PhD in France or in Germany?
it's a PhD in France.
In France, okay.
Yeah, it's the Chiffre program that you have with the universities.
Yeah, yeah.
And he's going to be paid by the company, and he's going to be developing the research work linked to the university, to the Polytech, to the University of Grenoble Alpes.
Yeah, it's very good. Yes, it's very good system for doing his PhD when you are in engineering science in France. I don't know if the same exists in Brazil, but it's a very good opportunity for him.
Unfortunately, we don't have like an institutional type of program like that. I wish we did, because, you know, the hardest part in Brazil is to find industries, to find companies that wish to develop research projects along with the university. Usually we do have like scholarships from agencies, from funding agencies in Brazil, or also from the university itself. But it's kind of more difficult to find like companies that will pay for the student like to stay 3 years doing only like a PhD work or a research work. But who knows in the future, when we get a little more mature in terms of our relationship with the industries, we might have that kind of initiative working. I think it's a very good program that you have in France, because, you know, you allow students to work directly on a problem, and in parallel you are developing research. So it's a win-win type of a relationship. That's very good.
Yeah, and they developed their network in order to find a position either in university or in companies. So it's pretty interesting for them. Yeah.
He was kind of, he was reluctant because he had like 2 offers for doing his PhD. The first one came from Schneider. That's where he's doing his internship right now. And the other one was at Paris Tech with Safran. But the second opportunity was more like a finite element modeling only, no experimental analysis, and his profile is more like an experimentalist. He likes to do like lab work, and he decided to go for the first offer with Schneider, and he's going to be staying in Grenoble, what is also a nice town. I've been there spending a few weeks with him in 2019 before the pandemics, and we spent like Christmas, and it's really a nice place to live.
Yeah, Grenoble is very nice in between the mountains. I think did he learn skiing?
Oh, he didn't. Well, he went just once, and but like we say, always carefully not to get injured, because we don't have that kind of sport in Brazil. Yeah. He's a very good soccer player, but skiing is maybe not his strongest ability. But sometimes he goes, and it's fun.
Okay.
Samuel, your audio is closed.
Oh, okay. Sorry. So I started the streaming, to transmit to people that are watching. And Teloli, you are streaming YouTube, not? No?
Yes.
So did you record in YouTube?
Yes, I will record it after the end of this presentation, and okay. Yes.
Okay.
Everything is.
So we're 18. I will send a message to Professor Drake with the link. I think it will be a problem, because yesterday he was writing us to ask to confirm the time, okay, and we deciding this time because the difference of time in United States e here in Brazil. I think we did.
I'll just go grab a cup of coffee right here, so I'll be gone for 30 seconds, okay, guys?
Okay, that's a good idea.
Yes. I'll take a little bit here.
Rafael, antes da gente começar, deixa eu te dizer uma coisa. Normalmente, quando eu tenho sugestões, ou coisas mínimas que são sugestões de texto, alguma outra coisinha, eu mando antes o PDF para o estudante, entendeu? Eu não mandei para você ainda, porque eu fiz as anotações em papel, à medida que eu ia lendo o seu texto, e a gente chegou agora no final do semestre, eu deixei só isso para passar limpo. E como às vezes eu escrevo anotações usando palavras-chave para depois eu lembrar o que eu quis dizer, se eu te mandar um scan do que eu escrevi à mão, você não vai entender. Então eu estou passando tudo isso a limpo, tá bom? Me dá mais uns dias aí, mas eu já te adianto que é muito pouca coisa, são mínimas sugestões que eu tenho, e eu vou te mandar isso na próxima semana, tá bom? Só dar um tempinho para eu fechar o semestre. Eu tô com 2 turmas, tô com 120 alunos esse semestre, então tá meio puxado. Mas embora você tenha nos mandado a tese com bastante antecedência, eu acabei deixando essa parte de passar limpo as minhas anotações para o final, entendeu? E aí ficou meio corrido agora. Mas eu te mando tá bom? Eu te mando semana que vem sem falta, tá?
Perfeito.
E aí você senta com o Samuel, dá uma olhada, mas já te adianto, cara, eu fiquei muito contente, muito satisfeito em ver a sua tese. Eu não esperava outras coisas de você, eu já venho acompanhando suas publicações, e então, assim, você está de parabéns, e te dou, assim, muito incentivo para você continuar em pesquisa de alguma forma, apesar das dificuldades que a gente tem aqui no Brasil, mas, assim, te incentivo fortemente a continuar fazendo pesquisa.
Muito obrigado, professor. Muito obrigado mesmo.
O Teloli tá de malas prontas, né?
Para onde ele vai? Para onde ele vai?
Olha,
Eu vou fazer pós-doutorado em Besançon, onde eu fiz parte do meu período de sanduíche, com o professor Gael também, o pessoal lá de Besançon.
Que bom, puxa vida, isso é ótimo, isso é ótimo.
Devo viajar em setembro.
A princípio, durante quanto tempo? 1 ano?
1 ano.
Que bom, nossa, excelente.
Mesmo sabendo, né, das dificuldades que a gente tem passando aqui, é muito realmente gratificante ter essa oportunidade.
Você vai sendo financiado por eles?
Sim, vai ser um financiamento, né, por lá, aprovado por lá. Eu não sei muito os detalhes, como funciona, né? Mas vai ser uma parceria, se eu não me engano, com uma empresa, um desenvolvimento de alguma tecnologia, alguma coisa assim. Eu não tenho ainda muitos detalhes, mas vai ser basicamente para continuar o que eu já tenho feito.
Muito bom.
Aí a hora que você voltar, já acabou a pandemia.
É. Tomara.
Teloli, what time is in the for meet professor break?
So I think that in Houston is about 2 hours earlier. You just have to confirm it. It is 7 a.m. 7 a.m.
I sent a message to him.
Ok.
I've completely forgot because I was asking. Normally, I ask the contact, the cell phone contact, and you have a meeting like this. And I forgot to send my phone contact.
Samuel, I am going to look into my contact because I think I got his cell phone.
Okay, that's better.
I can have a look now.
It's really complicated to decide a time because you have 3 different times: the Europe time, the Brazilian time, and the United States time.
Yes. Not so easy to manage
But you
the
know
schedule.
something? When I look at my Google agenda this morning, I copied the wrong link. I copied the YouTube link for the live streaming, and we got like 9 o'clock, and I was waiting, and all of a sudden I realized that I have to get the Google Meet link. Is there any chances that the professor might have connected to? Because you're already streaming, right?
Yes, I have started in YouTube. Just
We send in agenda the link to this room, and I send again now for 10 minutes ago. I send a message with my contact. I think Gael has the contact form.
Yeah, I'm looking for it, but unfortunately, I do not find it as easily as I expected.
I will take a coffee.
Samuel?
I think that he's taking coffee.
Okay, I found the phone number, but the one I got is 3 years old, I think, but let's try. I can send it to you, Rafael, or...
Okay, please.
Is there something to send some messages with the Google Meet? Yes, I think so.
Yes. Just have to click in the chat and then send us the...
I found it.
Okay.
Sorry. Okay, I think it's the good one.
Okay.
I'm not completely sure with the first number is +1. I'm sure, but
+1,
I don't know
okay.
if you have to write the 4 or not in US, because this number I used it in US only. So.
Okay.
But I think in US you got 10. Yes, 10 numbers. So this is 3, 6, 10. I think it's good.
Okay. I'll try to send him a message.
Sim, vou falar para quem está assistindo o streaming e a gente está apenas aguardando o professor Blake entrar. A gente está entrando em contato com ele e assim que ele entrar a gente dá início à defesa. And Gael, we have a new Brazilian student from Ilha Solteira now in Besançon.
Yeah, I hear about that. Yeah.
Rafael Raquete, that will take a PhD thesis with Professor Morvan.
Yeah. Morvan told me maybe I will be involved in the supervision. I don't know yet, but yes, Morvan said that he was very happy for that.
Yes, really happy.
the interview was really good. He told me here. So
yeah, he told me that we have 50 candidates and he is in first. And
yeah.
I'm really happy with this result.
We have a lot of candidates on the PhD position, but we don't have so much very good candidates. So we were very happy to have this one.
Yeah, Rafael Raquete, has a sandwich undergraduate in the INSA Lyon, so he has experience with the system education in France. So that's good.
And the experience shows that the integration into our French lab seems to be pretty easy for Brazilian students. Is it true, Rafael?
Yes, it's completely true.
So you did try, Rafael, to send a message to Professor Breck?
Yes, but I think that is not working, the number.
Did you try to find him on the WhatsApp with the phone number I sent to you?
Yes.
Yeah, I apologize for that. To be honest, I asked Pauline if she got the phone number because I lost it. But as we were together in Houston 3 years ago, she kept the phone number, but maybe this phone number is not available at the moment. I don't know.
I'm waiting for an answer. In fact, I don't know if this is the good number or not. Just a few more minutes to see if.
Okay.
I sent a message in the number that you sent me, Teloli.
He told that he's arrived.
He's online. He is online.
Yes.
He is online.
He said doing well, almost to work, and will be online shortly. I think that.
Oh, okay. He answered you.
It was the right number.
Yes, thank you.
Okay.
Daniel, when do you have some information when to restart the presential class in UFRJ?
Okay. In fact, some maybe 2 months ago, the dean had proposed a plan such that in the very beginning, only the experimental classes would start. So nowadays, the students from chemistry department, for example, they are taking classes, but only the lab classes.
Okay.
And the idea is that in October, all the experimental, all the lab classes would start in the uni, and next year all the students would start from. But Ministério Público is forcing all the students to come back on October, next October. Yeah. It's a problem because the rooms are not quite large, and we have some classes in which there are 70, 80 students, and so it can be a problem because I don't know if all of them will have access to the vaccine until October.
Yeah,
because they are very young, and
yes.
Perhaps they will have taken the first doses of the vaccine, but not the second one.
Yes, that's one problem.
Yeah, that's a problem. I don't know how it is in UNESP.
UNESP, it's really complicated now because UNESP, we are a multi-campus university in all the São Paulo state. So we are different places in different sanitary conditions. For example, there is some cities, some campus that you can restart some activities, but it's another place that's 1 month. And the complicate that's the system that the calendar is defined on the campus. That's one problem. That's one problem to restart. But I guess that in October and November we will start the presential class. In my point of view. But I don't agree with our governor, or Dória, with our governor, because he decided to reopen all the economy in August. I think it's really complicated because we have only the first dose in the most part of the people.
Sorry. Yeah, the point is this, because as in Brazil, the person takes 1 dose and needs to wait 3 months to take the second doses.
Yeah.
I think that the idea would be 1 month. You have to wait 3 months. And so for the younger, 18 years old, for example, here in Salvador, I think that people that are 35, 34 now are going to take the first doses. So I don't know, maybe in September, 18 years old will take the first doses. And so I don't know when we are going to take the second one. Perhaps only in December. So, I'm going to get my coffee and I will come back in 2 minutes.
Okay. Oh, Professor Brake. Hi, Professor Brake.
Hi, my apologies for being so late. I had the time
No
zones.
problem.
I thought we were starting at 8 a.m. Houston time, not 7 a.m. I'm so sorry for this.
No
Sorry,
problem. No
Professor.
problem. What's happened, because here we have 3 different times. We have a Brazilian time, the European time, and the USA time. So no problem. So welcome. Nice to meet you, Professor Brake. So,
Pleasure meeting you too.
yes, I would like to meeting the member jury. So the first is Rafael Teloli, the candidate. After Professor Gael Chevalier, that was the supervisor of the Rafael Teloli and his activities in the France in Besançon. Gael Chevalier.
Hi, Mathieu. How are you?
Doing well, Gael. Good to see you.
Professor Paulo Varoto from University of São Paulo. So back to break. And Professor João Antônio Pereira from UNESP. And Miss Samuel. Daniel will take a coffee. We are waiting some 2 minutes to start, and we can start the thesis. Before I will explain what happened, where is organized the defense in PhD in Brazil. So the presentation is organized in 3 steps. First, Rafael will present in 50 minutes, around 50 minutes. In the following, we start a discussion with the question made by the member jury. Everyone is free. You can ask the candidate. And finally, we'll have a meeting with the member jury to give the decision. Okay, that's the points. So we're waiting, Daniel.
Maybe Professor Paulo Varoto has a problem in his connection. I'm not sure.
He came back.
Yeah.
Yeah, my connection was down for a few minutes. Nice to meet you, Professor Brake.
Pleasure meeting you as well.
Okay, thank you.
We're waiting Daniel.
Now we are complete.
We are waiting Daniel.
Hello.
Oh, hello, Daniel.
Hello.
Oh, so let's start again. So, Daniel, I'm the pleasure to present to Professor Break, Professor Daniel Castello.
Hello, Professor Break.
So,
hello, pleasure meeting you.
Nice to meet you.
So let's start. So it's a pleasure to start the exposition of the thesis of Rafael Teloli, entitled New Contribution in the Analysis and Identification of Mechanical Systems with Hysteresis. The main jury is composed by Professor Martin Breaking from Rice University, Professor Daniel Castello from Federal University of Rio de Janeiro, Professor Paulo Varoto from University of São Paulo, Professor João Antônio Pereira from UNESP, and Professor Gael Chevalier, that was the supervisor of Rafael in France at Université de Bourgogne-Franche-Comté, and me as advisor in Brazil. So I would like to thank the participation of all the availability to contribute to the thesis. And now I will take the Teloli to start your presentation. Thank you.
Thank you, Samuel. Thank you to your members. I will share my screen. Okay. So, thank you again, Samuel, for your kind introduction. So today I will present my doctorate defense entitled as New Contributions in the Analysis and Identification of Mechanical Systems with Hysteresis. The outline of this presentation will cover the following topics. First, a brief introduction on our problem, then the use of frequency domain techniques for hysteresis models, the use of the high-order FRFs for structures assembled by bolted joints. Here I present an experimental application. Then this presentation goes through the experimental testing of dynamically excited jointed structures. Then the use of a non-parametric approach for predicting theoretical behavior of jointed structures. And finally, the final remarks. So, in general, jointed structures are widely used in industry, with applications ranging from wind turbines to the automobile or aircraft industry. Moreover, joints can also be seen as a design solution, in which one can propose complex geometries in a modular fashion. In some systems, the presence of joints is responsible for more than 90% of their structural density, and due to the properties on the surface connection, the joints can also be seen as a source of uncertainties in the motion of these systems. The main purpose behind using joints is to connect parts. However, when these parts are subjected to sliding motion, frictional effects may appear. As we increase the amount of slip, the nonlinearities becomes more prominent, such that we can say that the modal properties of these systems are amplitude dependent. Jointed structures are part of a multidisciplinary field, involving aspects from tribology, contact mechanics, structural dynamics, system identification, and also from micro to macro scale analysis. In this work, our interest is in dealing with structures assembled by bolted joints, in which we will deal with the nonlinear behavior of such structures. Then we can divide our problem into four quadrants, ranging from local to global scale of analysis and also from modeling to experimental applications. Regarding to the first quadrant here, one may propose the architecture of joints in terms of structure design, interface geometry, roughness on the surface, and also whether to use lubricants or not. As I said, our interest is in dealing with the nonlinear behavior of such systems. Then, the experimental setup considered must be the less invasive as possible to our system response in terms of vibration sensing, excitation design, and also boundary condition. From the modeling point of view, there are works in the literature that tries to approximate the interfacial physics at the micro scale. Moreover, general purpose finite element softwares also provide the necessary tools for encoding the relative motion between connected parts. Here we have two examples, the wall joint model and also the node-to-node contact. In both formulations, there is the presence of contact elements that are based on phenomenological hysteretic model. Here, in the last quadrant, in the fourth quadrant, we have works that try to encode the main factories of these structures based on global aspects of vibration. So here we will deal with isolated nonlinear modes by proposing lumped systems, for instance, to encode the main nonlinearities present in the response of these systems, in terms of, for instance, nonlinear damping and also nonlinear stiffness related to the softening effects. In this work, we will deal with these three quadrants here, in terms of architecture of joints, design of the experimental setups, and also modeling joints globally. The objectives of this work are to describe hysteretic systems by using analytical approximations, to apply frequency domain methods for predicting the response of structures assembled by bolted joints, and to investigate physics-based and non-parametric models to describe bolted structures, with insight on both uncertainties related to the measuring process and also the lab joint design. Introducing now the frequency domain techniques for hysteresis models, I will start presenting the smooth nonlinear operator. When subbodies are subjected to the sliding motion, we will see drawn in the restoring force displacement plane a hysteresis loop. One of the main properties behind it lies in the possibility of dividing the hysteresis loop into two different regimes, the loading regime and also the unloading regime. Based on the property that any bounded curve can be well approximated by a polynomial representation, we have proposed two bounding functions following this representation here. So here we have a representation to encode the behavior when we are in the loading regime of motion, and this function here to describe the unloading regime. But what is the motivation behind using a smooth nonlinear operator? In general, the most part of the phenomenological models available in literature to describe the hysteresis phenomenon are non-smooth. And due to this reason, it is not possible to approximate the solution of these systems by using a sum of series, using, for instance, the Volterra series. Here I have an example, which is the book 1 model. Here we have the inertial terms, the damping, stiffness, and here the hysteretic restoring force that depends directly on its time derivative, such that here alpha, beta, gamma, delta, and epsilon are the book 1 power meters. Note that here we have the presence of the modular function. As I said, we can divide the hysteresis loop into two different regimes, especially for the book 1 model, we can divide it into 4 different equations. When we assume this value equal to 1, we can rewrite the restoring force of the book 1 model following these 4 relations here, in which Z1 and Z2 are responsible for encoding the unloading regime of motion, and Z3 and Z4 to encoding the loading one. Note that here, the expressions of the restoring force paths are given based on this term here. This is exponential term. We must substitute this term here in order to provide an explicit relation of the restoring force in terms of the displacement. In this case, we have proposed to approximate this relation by using the Taylor series as a smoothing procedure, such that now we can represent these restoring force paths based on a polynomial approximation. Based on these equations, we can now propose an equivalent nonlinear model to represent the book 1. Here we have our nonlinear operator, which is given according to these bounding functions here. So we will have one function to describe the loading regime of motion and another one to describe the unloading regime. The transition between these both functions is given according to the sign of the time derivative of our excitation input u. Note that here we have the lambda coefficients of our polynomial form, and due to the presence of the symmetry in the hysteresis loop of the book 1 model, the absolute values of these coefficients are equal. So lambda 0 here, it's equal in absolute value with this lambda 0 here. Due to this reason, we can propose now, we can represent these coefficients as an explicit function of the book 1 power meters following this relation here, in which now we have expressions for the coefficients lambda 0, 1, 2, and 3. Note that here, these parameters, in addition to the book 1 power meters, are given as function of the maximum displacement in the hysteretic restoring force y, and here also as function of the threshold displacement y0 that corresponds to the opening of the hysteresis loop. We can combine that bounding functions to a single expression following this relation here, in which this parameter is given according to the transition with regard to this sign here, and we will see this parameter u0 as an additional input to our problem given as function of the parameter lambda 0 and also as function of the sign of our time derivative of our excitation force. Since that our interest is in smoothing the hysteretic restoring force, we will approximate this additional input by the Fourier series approach. So here we have the Fourier series approach to this input here, represented in the exponential form. Now that we have a smooth formulation for representing the book 1 model, we can introduce the Volterra series that we will use to approximate the solution of our system. So here, one of the main advantages in dealing with the Volterra series lies in the possibility of dividing the nonlinear output of a system into linear and nonlinear contributions. It is important to point out that the linear contribution corresponds to the impulse response function for linear systems. Each of these contributions can be computed based on this relation here, in which we have the convolution between the Volterra kernels and also the multiple inputs considered in your problem. As in the linear case, we have the frequency counterpart, the so-called frequency response curves, the frequency response functions. Here we also have the counterpart for the nonlinear case, which are the multidimensional, which are the high-order frequency response functions. To obtain these functions, we apply the multidimensional Fourier transform on the Volterra kernels following this expression here. One of the main advantages in obtaining the expressions for these functions here is due to the possibility of rewriting these functions as explicit functions of the parameters from our motion equation. We can derive these analytical expressions to these kernels based on the harmonic probing method. Assuming now that we have a singleton input, which is given by this relation here, we will assume that two terms on the Fourier series will be enough to describe our problem. Then we will arrive at this relation here. So then, substituting U0 and U in our motion equation here, we will propose this following solution. So here we have the solution based on the Volterra series representation. Here we have the linear contribution, and here the nonlinear contributions. Since that we have already substituted our excitation terms in this equation, we have now the first order solution that is given according to this relation here. So you have contribution with regard each of these inputs. So here you have the contribution related to this input, related to this input, and also this one related to this input. Obtaining the time derivatives of these terms and substituting in this equation and then balancing the exponential terms, we arrive at the algebraic expressions for our high-order frequency response functions. So here we have our first kernel, which is given according to this expression here. Note the similarity between this expression and the FRF of linear systems. Moreover, the expressions of these parameters are given as explicit function of these model parameters, as I already said. Also, we have here this relation with a shift of 3 times in the frequency in relation of this equation here. Now we can perform, we can predict the response of our equivalent system by using the Volterra model. We will consider here the Boltzmann oscillator with these model parameters that were obtained from this reference here. The solution of our system was obtained based on the numerical integration by using the 4th order Wunsch-Gutta method. Here we have the direct comparison between the response from the Boltzmann oscillator and the Volterra model in red. Note that here the Volterra model could predict with good agreement the response from our Boltzmann oscillator. Here we have the power spectrum density of our response to highlight the presence of high-order harmonics in the system response. Here this harmonic corresponds to the excitation frequency. Here you can see the Volterra contributions, in blue the linear contribution, in red and black the second order and the third order contributions respectively. Here we have the power spectrum density of each of these contributions to highlight the presence of the high order harmonics. Now, by comparing the hysteresis loop predicted by the Volterra model, it is clear that the Volterra model can predict the hysteresis loop when the hysteresis loop is almost closed in these two figures here. However, when we increase the excitation force, note that the Volterra model starts to present convergence problems, which becomes more clear when we have a look in this figure here, which corresponds to the frequency response curve. Note that in the vicinity of the resonance frequency, the Volterra model could not predict the behavior of the Boltzmann oscillator. Another way that we have to approximate the solution of the Boltzmann model is based on the harmonic balance method. In this framework, we will assume that the nonlinear response of our system can be projected by following the Fourier series approximation following this relation here. Moreover, the restoring force can also be formulated based on the Fourier series following this expression here. Substituting both terms in our motion equation and assuming that we have an harmonic input, we will find this system of equations here. However, Note that in the hysteresis loop of the book 1 model, we have 4 different restoring force paths. Thus, we must consider this particularity when we will compute the coefficients of our harmonic in the harmonic balance method. So here, since we are considering the harmonic excitation, the transition between each of these restoring force paths will be given according to the time period of each of these first terms here. Moreover, we will consider the Taylor series approach to provide a polynomial representation of each of these restoring force paths here. Here we have some results from the response predicted by the harmonic balance method. Here we have the frequency response curves. In black, we have the Fourier series considering the fundamental harmonic, and in blue, we are considering the fundamental aided to the third order harmonic. Note that here we have a zoom around 1/3 of our resonance frequency, in which when we consider 3 terms on our Fourier series approximation, it can provide a good representation from our Boquin oscillator. Here we are around the subharmonic component. This is why we have these amplitudes more pronounced around this frequency interval here. By assuming 3 terms in the harmonic balance approximation, here we have this hysteresis loop predicted by our analytical solution around 1/3 of the resonance frequency for low and high excitation amplitudes. Here we have the response in the time domain that highlights the presence of harmonic distortions on our response. And here we are considering this hysteresis loop predicted when we have the excitation frequency at our resonance. So here for low excitation amplitude, and here for high excitation amplitudes. Also, we have the time response, in which we can see that the harmonic balance framework could predict the behavior of the Boquin oscillator better than the Volterra model. As final remarks related to this section, the smooth procedure proposed here can be an interesting alternative solution to deal with theoretic systems. With regard to the Volterra series, this was the first application exploring the use of Volterra series harmonic probing algorithm and also system with hysteresis. However, we still have convergence problems, but even so, the higher order FRFs provide a good framework for parameter estimation. We will see this topic in more detail in the next section. With regard to the harmonic balance method, it performs better than the Volterra model, especially for high amplitude levels and in the vicinity of the resonance frequency. We still have convergence problems, but this approximation paves the way to the possibility of analyzing nonlinear modes in systems with hysteresis. Further details on this section here can be found in these both papers. Introducing now the use of the high order FRFs. In this section, we will deal with an experimental application. In this case, we have some ingredients. The first one is that our experimental test bench presents softening effects in the vicinity of the resonance frequency. Moreover, since that our measurements are performed during different days on the same week, we have also data variability. And due to the presence of a joint connection, we have the presence of the hysteretic restoring force actuating on our system. Thus, to deal with all of these problems here, we have proposed a stochastic version of an equivalent Boquin model for modeling the first vibrating mode of an assembled structure. We have used the high order FRFs for parameter estimation, and since that we have data variability in our measurements, we have considered the Bayesian paradigm for updating the model parameters. So here we have the Boquin model that we used in this application, in which here we have the damping ratio, and here we have the resonance frequency, here we have the hysteretic restoring force, and also its time derivative. Just introducing a theoretical background, we have this equivalent nonlinear model, but we have saw that the Volterra series performs well only when the hysteresis loop is almost closed. So when we have this condition, these 2 terms related to our additional input and this term here, quadratic, will be equal to 0. And then we will arrive at this new relation here. By approximating the response of that system by using the Volterra series, we have derived the analytical expressions for the high order FRF. So here we have the first order Volterra kernel, which is given based on this relation here, and our resonance frequency is given according to this stiffness term here, and also our coefficient lambda 1. With regard to the third order Volterra kernel, we have this equation here, in which this kernel is given as an explicit function of our first order Volterra kernel and also the coefficient lambda 3. These both coefficients are given as function of the Boltzmann parameters alpha and also delta. The Volterra series representation using three contributions is given based on this relation here, in which this term here corresponds to the first order harmonic amplitude and this one corresponds to the third order harmonic amplitude. Both harmonic amplitudes can be filtered out from the total experimental response using, for instance, the Fourier filtering. We can compute our experimental third order Volterra kernel by using our third order harmonic response and also our excitation input considered. So here we have the relation to obtain the experimental version of this kernel, and based on it we can update the Boltzmann parameters by using this analytical approximation here. So we will use the experimental measurements to then update the Boltzmann parameters. Since that we are dealing with a problem that presents data variability, we will consider the Bayesian inference strategy. In this context, before introducing the Bayesian inference strategy, I will put three assumptions. The first one is that the parameters are random variables and the system observations are also random. A prior distribution is assigned and a likelihood function is obtained from some hypothesis of the process. Here, this hypothesis will come from the nonlinearities of our system. We will then update the prior distribution into a posterior one. So here we have the bias theorem, in which this term corresponds to the prior probability, to the likelihood function, normalizing prior probability, and then the updated posterior probability. It is important to point out that if we assume a prior distribution, then our posterior distribution will be proportional to our likelihood function. In this application, we will consider these random variables, our damping ratio, the stiffness term, and also the Boltzmann parameters. So here we have the expressions of the likelihood functions. Here we have the third order Volterra kernel in direct comparison with our kernel measured experimentally. Note that these parameters, we will obtain the PDFs related to them by using the condition in which the series loop is almost closed. Then, to update the remaining parameter, the parameter gamma, we will consider experimental conditions, experimental excitations, in which the series loop starts to become more pronounced. So here we have the expression in which we will update the Boltzmann parameters based on these parameters already identified, and then compare the numerically integrated response with our experimental response. For updating the PDFs, we have considered the Monte Carlo Metropolis Hastings algorithm. Thus, the flowchart of this identification framework may be stated as follows. In step 1 comprises the data acquisition. In the step 2, we will consider the linear regime of motion by applying a white noise excitation. We will then perform a model testing, compute the initial PDFs related to our resonance frequency and our damping ratio, and then compute our first order kernel. We will use this to update our third order Volterra kernel at this step here. With regard to the step 3, we will perform probing tests to filter out the harmonic components by using the harmonic filtering. We will then compute the third order Volterra kernel experimentally and then update the Boltzmann parameters following this relation here. In this step 4, we will update our computational model based on these parameters to finally identify the parameter gamma following this relation here. We will then evaluate our computational model and then validate it by comparing the hysteresis loop predicted by our computational model and from our experimental measurements. Here we have the experimental setup proposed in this section, which consists of a cantilever aluminum beam. Here we have the shaker, which is attached close to the clamped end of our structure to minimize the shaker structure interactions. Here, since we are interested in dealing with the first vibrating mode of this structure, we have measured the velocity at the tip of the beam by using a laser vibrometer. Here we have the top view of our plotted joint, and here we have the schematic top view of our experimental setup that highlights the dimensions of our problem. In this work, we have considered the shaker operating in the voltage mode, in which the voltage supplied in the shaker amplifier are always constant. Due to this reason, we have adopted these values of voltage and then transformed them into force values. The tightening torque applied in both bolts was 5 Newton meter. Here we have the initial results from our structure by considering a random excitation with low excitation amplitude. Here in blue we have the mean FRF, and in gray we have the 99% of confidence bands that highlights the data variability present on our data. Again, it's important to point out that we have considered the experimental runs performed during different days at the same week. From these curves, we have updated the parameters, the damping ratio, and also the resonance frequency. Here we have the mean values, and here we have the coefficient of variation that is based on the standard deviation and also the mean value. Note that the variation with regard to our resonance frequency is slow. However, the variation on the damping is very high. Due to this reason, we will let this parameter free to be identified on the next identification step. Here we have the third order Volterra kernel. In red, the kernel computed experimentally. Here we are around 1/3 of our resonance frequency because at this frequency interval, the third order harmonic is more pronounced. We are considering high excitation levels, and here here we have the prediction performed by the analytical expression. From this curve, we have updated the parameters damping, the damping ratio, and also the Volkmann parameters. This corresponds to the MAP value, that is the maximum a posteriori value, and here we have our mean values obtained from these curves. Here we have the coefficient of variation. Note that in all of these three cases, the coefficient of variation is very low. Due to this reason, we will set this parameter as constant to the next identification step. Note that here we have updated the damping ratio due to the presence of this parameter in our analytical expression of the third order Volterra kernel. Here we have the PDF for the damping ratio. In blue represents the PDF estimated after the model analysis. Then in red we have the uniform PDF, and in black we can see how this PDF evolved to the posterior one. Again, the PDF but of the parameter alpha and of the parameter delta. Substituting these parameters and updating our computational model, we can now identify the remaining parameter, that is the parameter gamma. We have considered the sweeping sign test around the first vibrating mode with high excitation amplitude to highlight the nonlinearities in our system response. So here we have the PDF, and here we have the updated values based on this likelihood expression here. Then performing a model verification. Here we are considering a direct comparison with our computational model with experimental measurements by using a white noise excitation at low excitation level. We can see that here the confidence bands of our model could accommodate well our experimental measurements. Here, by considering a sweep sign test with low excitation amplitude, and here by considering a sweep sign test but with high excitation amplitude. Note that our computational model could predict with good agreement our experimental response. Here we have the hysteresis loop predicted by our computational model for low excitation level 0.05 volts, for 0.10, 0.15, and 0.20. In all of these conditions, we can see that the confidence bands of our model could also accommodate well the response from our experimental test bench. As final remarks related to this section, the high-order FRFs can be an useful framework for model updating in applications for analysis of weakly theoretic systems in which the hysteresis loop is almost closed. The stochastic Volkmann model could reproduce with good agreement the output from the experimental test bench. As next steps, to perform tests increasing the data variability, for instance by considering the complete assembly and disassembly of our lab joint, and also to extend the proposed methodology to deal with multi-degrees of freedom systems. Further details on this section can be found in this reference here. Let's introduce now the experimental testing of dynamically excited jointary structures. Here we will propose a new benchmark, so-called Orion beam. In general, it is difficult to achieve damping and stiffness at the same time, since that for enhancing damping, low contact pressures are necessary. The contact pressure is directly related to the tightening torque applied on bolts. Thus, if you reduce it, the stiffness will also be degenerated. To avoid this problem, we have proposed a structural design in which bolts are playing different structural functions. We will have bolts playing static functions to ensure structural stiffness, and also bolts to perform damping functions to increase the frictional dissipation. From that, we want to see, we expect to have amplitude attenuation without significant changes on our nominal frequency. To approximate the response from our experimental setup, we have proposed a Duffy-van der Poel model. It is important to highlight that the name Orion beam derives from the Orion constellation. Here we can see the Orion's belt that has 3 stars, just like our lap joint has 3 bolts, like this, like it is illustrated here. So here we have the illustration of our experimental setup. Again, our shaker is attached closer to the clamped end of our structure. We will use a load cell to measure the force applied by our shaker. Here we have the central bolt that will always consider a fully tightened torque condition, and here we have the external bolts in which will vary the tightening torque applied. Here we have an schematic representation from our system, and here we can see the values of tightening torques applied. The central bolt will always hold a tightening torque of 80 cm to ensure the structural stiffness of our system, whereas the external bolts will vary the tightening torques into 80, 30, 20, and 10 cm. Note that here we have the presence of contact patches to reduce the contact area and then to minimize uncertainties related to the contact surface. It is important to point out that the frictional effects are amplitude dependent. Then, to characterize how different torque values will influence the structural behavior, we have performed step sign tests around the resonance frequency. To minimize underside effects related to the excitation, for instance, the drop-off phenomenon, we have considered this feedback controller here to control the force applied on our structure. The main idea behind it is to generate a control signal to send it to our shaker. So we will send a voltage to our shaker. The shaker will excite our structure. Then we will measure the force applied by using a load cell. Then we will compare the force measured by our load cell with the desired force in our set point. Then we will perform the amplitude correction and perform this feedback controller until the convergence of the force value. Here we can see an example that highlights the necessity of increasing the voltage supplied on our shaker when we are close to resonance frequency. Note that here, to keep a constant excitation force, we must increase the voltage supplied in the shaker. Here we have an example of the constant force measured by our load cell, and here we have the interactions until convergence on our feedback controller. Let's now introduce some dynamic response from the Orion beam. Here, the structure was subjected to the white noise excitation and considering a monolith condition. In the monolith condition, we will consider that the contact packs will be glued. Here we have the frequency response curve, and here we have an illustration of the modes by considering 195 sensing points. To evaluate the design choice performed in our work, we are interested on the vibrating mode that promotes pronounced deformation, especially around the lap joint. So then we have selected the 6 bending mode due to the observability purpose. From now on, we will consider stepped signs around this frequency range, considering several excitation amplitudes, 10, 50, 100, 150, 200, and also this last value here, by using this frequency increment, and we will measure these representative quantities. The first one, which is the resonance frequency, it is directly related with our structural stiffness, and these other two, the peak amplitude and also the half power bandwidth, are two quantities that we can measure indirectly the damping of our system. So here we will first verify the repeatability of our system. Here we are considering the complete assembly and disassembly of our lap joint several times with a torque applied on the contact packs of 80 cm. Here considering a low excitation force and here a high excitation force. Note that the parameters related to the damping are more sensitive to the variations on our process of assembly and disassembly. Here we are now considering a tightening torque of 20 cm and also an excitation level of 10 millinewtons, in which is supposed that our structure is linear, presents the linear behavior. So here we have the condition with disassembly and here without disassembly. Note that with disassembly, when we have low values of the tightening torque, our response becomes more uncertain due to the uncertainties related to our surface and also to the pressure distribution on our contact surface. Here we can see that in this condition with disassembly, our variation is more pronounced than in this one without disassembly. Now performing an analysis on the influence of the tightening torque. Here we have the excitation force of 10 millinewton, in which is supposed again that the structure behaves linearly, but by considering several values of torque. Here we can see that as we decrease the value of torque, it is possible to see that the price stress caused by the tightening torque applied changes the behavior of our structure in frequency. Here you can see a shift in frequency and also in amplitude. We can see that the attenuated amplitude here, we have more amplitude attenuated in this condition than in this one. Now, verifying the influence of the excitation force. Here we have the excitation amplitude with different gradient colors, in which two factors can be highlighted. The first one is that as we increase the excitation force, our structure starts to present the softening effect that is characterized by the decaying of a resonance frequency here. Moreover, we can also see the amplitude attenuation, okay, related to this. So here we have our curves related to the 10 cm torque, 20, 30, 80, and also we are comparing with the glue condition. We can now perform a quantitative analysis based on these figures. Here we have the evolution of the resonance frequency as we increase the excitation amplitude. Note that here we can see the resonance frequency decaying due to the softening and stiffness. The softening occurs due to slip, due to increase of the amount of slip that occurs in the contact packs. You can see here the resonance frequency and here the amplitude. A similar trend that we had in the resonance frequency, we also have in the amplitude attenuation, which is clear with these curves here. And here we have the evolution of the -3 dB bandwidth. There is an increase on the bandwidth as we increase the excitation amplitude. From these curves here, we can perform some remarks. The first one, with regard to the bandwidth evolution, it depends on the energy dissipation by the frictional effects that occur on the contact patches and also due to the presence of the softening stiffness. With regard to our resonance frequency and also our amplitude attenuation, here we have compared the first value of frequency and the amplitude attenuated, the first value considering low excitation amplitudes with the last one considering the highest level of the excitation amplitude. Note that variations in terms of our resonance frequency are low, around 1%. However, we have a greater variation here in the attenuated amplitude. Due to this reason, we can see that it is possible to have an attenuated amplitude without compromising the structural stiffness of our system. Let's now introduce the Duffy-van der Poel oscillator to investigate the nonlinear behavior of the Orion beam. If we draw a parallel with reduced order representation of finite element models, we will see that this first term is equivalent to the inertia, to the damping, to the stiffness, to the nonlinear damping, and also to the nonlinear stiffness. Here, phi corresponds to the mode shapes, m to the mass stiffness and K to the stiffness matrix. Mass is mass matrix and stiffness matrix. To identify the model parameters of our Duffy van der Poel oscillator, we have proposed this solution here based on the first harmonic on the Fourier series representation. Substituting these terms here and by using the harmonic balance framework, we have arrived at these relations here, in which, based on the pseudo-inverse of this matrix, it is possible to extract the model parameters related to this motion equation. So here we have the identified parameters for the glue condition. Okay, so here we have the values of mass, damping, stiffness, nonlinear damping, and also nonlinear stiffness. Note that the nonlinear stiffness has negative value due to the softening effect that we have on our restoring force. Here we have normalized all of these parameters based on the glue condition, and we have saw how it was the evolution of these parameters as we decrease the tightening torque applied on the bolts. So here it is clear that when we decrease the tightening torque, there is an increase on our damping, which was expected. However, when we see the evolution of the parameters M and K, we can see that there is also a decrease in these parameters as we decrease the tightening torque. However, if we look at this relation here, the mass and also the stiffness matrices, they are constant. Then the variations on these parameters are related to the nonlinearities on our mold shape. Here we can see the evolution of the nonlinear parameters, the evolution of alpha and also the evolution of beta, which becomes clear that when we decrease the tightening torque, the nonlinear behavior of our structure becomes more pronounced. Here we have an evaluation of the proposed model represented by the dashed lines, and the solid lines represent the experimental measurements. As final remarks related to this section, the contact packs minimize the dynamic clearance and provide a contact pressure slightly sensitive to shape imperfections. So we have ensured interesting measurement-to-measurement repeatability. We proposed a design in which it is possible to benefit of amplitude attenuation without significant losses in the contact stiffness. Moreover, we have proposed the use of the Duffy van der Poel method, which performs well. As next steps, the lap joint configuration suggests further investigations into new control techniques in jointed structures for amplitude attenuation based on the applied bolt per load. Again, further details on the methodology presented throughout this section, the interested reader can find in this both reference here. Let's introduce now the use of a non-parametric approach for predicting the theoretical behavior of jointed structures. Just introducing the problem, in some applications demand less expensive computational cost, for instance, for decision making or to verify the design choices. In this context, black box approaches that do not depend directly on the physical parameters are a good choice. Then, in this section, we have proposed a machine learning Gaussian process regression model with the NARCS framework to emulate the response of a system of interest with natural probabilistic confidence intervals on our model proposed. Consider a general regression given by this relation here, in which one intends to represent the process observations y based on a mapping function f and also an input vector x. Here, epsilon is the inherent randomness in the observations that is assumed to be Gaussian distributed with zero mean. In this work, we use the Gaussian process to represent such a relation. The main advantage in using this regression is that the Bayesian inference is performed directly on the functional space, which reduces the overparameterization problem. We could select any type of function to represent this function here, but in this work, we have considered the NARCS framework to emulate this theoretical behavior of the applications investigated here. Thus, X will be formed by the regressors in both the excitation signal y and also in our system response. Based on that, F is formed by the assumption of a multivariate Gaussian prior distribution of zero mean. The construction of the model depends directly on the training data considered. Thus, we have considered here signals that contain the main factors related to the nonlinearity of the systems of interest. Here we have the joint distribution, in which f star is the predicted function at new input samples. Then the Bayesian inference is performed to condition a posterior predictive distribution, and from that we have obtained the posterior predictive mean and also the posterior predictive variance. Here we have the choices of the covariance function. We could have selected any kind of covariance function, but in this work we have proposed these both. Then, based on this, we have used a new additive kernel given by the sum of these both covariance functions. Then we have performed the update of these hyperparameters based on the maximization of our marginal log likelihood, given by this relation here. In this work, we have considered the gradient method to perform the update of this parameter, in which here k, it is different from in the last case. K here is the covariance function. Then the identification framework of this work may be stated as follows. The first step comprises the data acquisition, in which we will consider subsign tests, pure sign tests, and also tests with the white noise. Here we will train our model to optimize these hyperparameters and also to estimate the lags. To perform it, we have considered this metric, which compares the solution, which compares the experimental measurement response with the model predicted mean. After obtaining the model predicted output and also the standard deviation, we will perform Monte Carlo simulations in this step 3 to verify the performance of our model. Here we will first perform a numerical assessment of our GP-NARX model based on the Boltzmann oscillator, which is given again according to this relation. We have considered these model parameters, and here we have the training data considered for the optimization of the lags and also to optimize the hyperparameters. It is important to highlight that here the input signals have the same characteristics, but we have considered different excitation amplitudes. From here, the training data was considered by using a subsign test around this frequency with low and high excitation amplitudes, and to perform the lag optimization, we have considered subsign tests with a medium excitation amplitude. Here we have the output-input surface with relation of our value of fit. Here we have our surface, and here we have projected this surface, in which here we have the output lags, and here we have the input lags. The red line, the red dot, corresponds to 20 lags in our output and 17 lags in our input. Based on these values, we have found a value of fit of 92%. So here we have the verification of the response from our model considering a subsign test with high excitation amplitude. In blue, we have the model mean response. In gray, we have the model predicted output. And in red, we have the Boltzmann data that was computed by using numerical integration scheme based on the fourth order Mesquita method. Here, we are considering a different excitation signal than we have used for the training step. Here we have the pure sine, considering an excitation frequency at the resonance frequency with a high excitation amplitude. In blue, we have the model mean response. In gray, the model predicted output. And again, in red, the Boltzmann data. Here, we can see the white noise input with high excitation level, in which it's possible to see that the further away the training data one wants to predict, more uncertainty will be present on the model's response. We can see that the confidence bands in this application are larger than in the other case, because the signal considered here is different from the harmonic signals considered during the training step of this algorithm. Let's now introduce the use of the GP-NARX model to represent this experimental setup. Here, as training data, we have considered sweep sign tests around the first resonance frequency with low and high excitation amplitudes supplied on the shaker amplifier. We have performed the lag optimization, considering also a subsine test, but with an amplitude of 0.10 volts, a medium amplitude level. This was selected to improve the model predictive capability. So again, here we have our surface based on the output lags, input lags, and also on our value of fit. In red, we have the 16 terms in our output lags, 10 terms in our input lags, that corresponds to a 96% on our value of fit. Here we have the direct comparison with the response predicted by the GPNARX model with our experimental data. With regard to subsine test with high excitation amplitude. Note that here the model could, the confidence bands of our model could accommodate well the experimental variation from our experimental test bench. Here we are considering a different excitation input. Here I put a pulse sine at our resonance frequency with a high excitation amplitude. Note that here, due to the harmonic characteristic on our input, the model could predict well the response from the experimental test bench. And finally, by considering a white noise input with high excitation amplitude. Note that here the confidence bands are larger than before, but the mean, the model mean can reproduce well the behavior from our experimental data. As final remarks related to this section, the black box model is trained to take into consideration the main aspects present in the dynamics of theoretic systems. Numerical and experimental data were successfully correlated with the model predicted outputs. The GPNARX model could also accommodate uncertainties related to the experimental measurement process, as we saw. As next steps, we will explore the use of the GPNARX model for structural health monitoring purposes to detect the loss of tightening torque. Again, further details on this methodology can be found in this reference here. As final remarks, we have proposed in this thesis new approximations, new closed form solutions through the Volterra series and also through the harmonic balance method for predicting the behavior of theoretical systems based on a smoothing procedure by using the Taylor series. We have used the high order FRFs for model calibration, taking into account experimental variations. Here, due to the presence of data variability, we have adopted the bias inference strategy to update these functions. We have also proposed a new benchmark, the Orion beam, in which was possible to promote the amplitude attenuation without compromising the structural stiffness. We also have proposed the use of the GPNARX model for predicting the nonlinear behavior of systems with hysteresis. Then, based on the results explored by this doctorate defense, the perspective of future works are to propose a vibration reduction based on assembly structures by using the control of the tightening torque applied on the bolts, to explore especially the GPNARX model for ACHM applications of bolted structures, and then based on the non-smooth operator and also on the Boltzmann model, to propose new approximations for predicting the internal rolling displacement of tires. I would like to thank the financial support provided by FAPESP with these grant numbers, to my advisor, Professor Samuel da Silva, to my co-advisor, Professor Gael Chevalier, and also to the collaborators of this work, Professors Pauline Butot, Thiago Rito, and Professor Michael Todd. Thank you for your attention.
So thank you very much, Rafael, for a nice talk. Let's begin the discussion. Firstly, I would like to invite Professor Boaken. And again, thank you very much for your participation. We're really happy to contact with you in this day. And you have the time during CAR to do the class to tell all about your comments and suggestions. Welcome.
Wonderful. Rafael, first of all, fantastic job. I very much enjoyed reading through your thesis and listening to your presentation just now. I've got a lot of comments that I'll share with you at a later time because some of them are nitpicky. But you know, my overall impression is you've done a great job. But I do have a couple more fundamental questions for you right now, if that's okay. first of all, with your identification method that you talked about in chapter 4 and you showed towards the beginning of your presentation, it seems like you're treating the system as a linear system. And what I mean by that is you specify zeta as a constant variable. It's an uncertain variable, but it's constant. It's not something that you're considering as being able to change with amplitude. So I'm wondering, how do you reconcile that with everything that you learned in chapters 2 and 3 about the amplitude-dependent nature of these nonlinear systems?
Okay, I will just consider this. In this chapter, I'm right? With regard to this model here. So, sorry, it is with regards to the Bookman model, this Bookman model here proposed.
Sua tela não está aparecendo.
Sorry, I forgot. Okay, sorry. Here it is. Okay.
Perfect.
Yes. Okay. In this case, okay. To explain, yes. Here the amplitude dependence we have captured based on the theoretical return first of the book model, due to the mathematical relations on our proposed model. These parameters, when we identified them, they could adjust the experimental response. With regard to our identification framework, we have considered not the linear case, but a condition in which we have a weak theoretical behavior, because we must be at conditions in which the hysteresis loop is almost closed. To perform this, we have considered an excitation force around 1/3 of our resonance frequency. At this condition, the harmonic distortions related to the subharmonic becomes more pronounced. From that, we can still see the nonlinear behavior of our system, but with this hysteresis loop closed, we can see this relation based on the results from my thesis. So here I have a comparison between the harmonic amplitude. Here we have the harmonic amplitude, the first order harmonic amplitude, and here in red we have the third order harmonic amplitude. So if you have a look at this value here, they are lower than the maximum amplitude found even in this relation here. So here we are almost 3 millimeters as maximum displacement amplitude, and there we are around 1 millimeter. Since the amplitude dependence of our nonlinear system will give the opening or not of our hysteresis loop, we have assumed that at that conditions the hysteresis loop is almost closed. I don't know if it was clear.
That answered my question. I think that maybe, so let me see if my understanding is correct. So in looking at the Bach-Wien model, you have a linear viscous damping coefficient zeta, and then the nonlinear terms are the cubic spring term and the other term you've got it there. So it's okay that you're treating it for this system the way you do. Okay. Since you've got your thesis open, let me ask one quick question about your thesis before we jump back to the presentation. Could you go back to figure 41 and 40? You kind of scrolled by those a few moments ago.
Okay.
And the reason why I want to look at these two figures is because I thought these two figures were for the same system. Here's one of them.
Okay.
So this is showing a softening behavior, right? Figure
Yes.
40b is softening behavior. But if you go to figure 41 for the same system, you're showing a stiffening behavior. Yeah,
okay.
right there. So I think I might have missed this in the text. Can you explain to me why 40b shows softening, 41b shows stiffening?
Yes, of course. So here we have considered in this figure here step sign tests. Here, this figure this figure here, it is equal to this one, to the black one. So
Okay.
we are seeing the degradation of our FRF due to the nonlinearity. So it looks like the hardening behavior, but if we compare with the linear case, we can see that the stiffness, the resonance frequency is in fact decaying. So it is the same figure that here the black in the black curve.
Okay, that makes sense. Thank you for explaining that.
You're welcome.
So, kind of one of the general themes and the questions I'll share with you later about comments on your thesis is I was hoping for more details on the experiments. And so I've got a whole list of them, but maybe some of the more important ones to ask. How did you enforce the bolt torques that you went with? Because you had very specific bolt torques of 20 centinewton-meters, 80 centinewton-meters. How did you prescribe those bolt torques?
So we have used torque wrench. So at each experimental run, I have checked the value of torque applied on these bolts by using a torque wrench. In both applications, in fact, even here in the Orion beam and also in the last figure that I have shown, this one.
So
I haven't used an instrument to measure this in a real time. I haven't considered this. I have only measured this after each experimental run.
Okay, so the reason why I'm asking this question is torque wrenches are notoriously unreliable. You know, we did a study looking at looking at the strain in bolts after torquing them up to a prescribed level, and generally, you know, for us, you know, we typically tighten things up to like 20 newton meters, so a lot higher.
Yes.
But nonetheless, like we found that the average strain in the bolt was like 40% of what we were expecting it to be. And the standard deviation was almost like 35% of nominal value. So the torque wrench introduced a lot of experimental error for us that we later had to correct. And I'm kind of curious if you tried to account for this or understand this, because I see that you've got some plots of variability. You've got one really good figure looking at, you know, this is the variability from assembly to assembly when you disassemble them and put it back together. And this is the variability from measurement to measurement where you just loosen the bolts and retighten them again. So I'm wondering if you could comment on that at all. Yeah, that figure, exactly.
Yes, in fact, in the thesis, I have included a table in which these experiments were performed with help of Professor Pauline Buteau. She have performed at first measurement of force applied on each of these bolts, and we have found these values here. So yes, in fact, she measured the variation on the torque applied by each of these bolts, and here in this table, the table 4, we can see the variation with regard to each of these torques and also the force applied. So yes, in fact, we can see that as we decrease the value of the torque applied, we have more uncertainties related to our torque wrench. So yes, you're right. As we increase the value of torque, this variation becomes less pronounced. So here we can see in this table.
So just following up to this, I think this is something I might have missed. You had a force cell in there at some point, right? Where you actually were measuring the force on the bolts.
Yes, before starting.
Okay, fantastic. That answers the question. That definitely helps a lot with giving confidence then.
Okay.
About what you did. The next question I have is regarding your conclusions from studying the Orion beam. So, you know, this is a quote from your conclusions. It is possible to improve energy dissipation in bolted systems without compromising their integrity just by tuning the tightening torque properly. So, as a tribologist, I have a lot of concerns with that statement, because as you lower the tightening torque, the dissipation, the added dissipation in your system is coming from interfacial friction.
Okay.
And that interfacial friction manifests itself as fretting. fretting fatigue, fretting wear, which means that if you're going to increase the damping by lowering the torque on the bolts, you are going to dramatically shorten the life of the beam because you're dramatically increasing the fretting fatigue of the beam. I was wondering if you could comment on that at all, or maybe think about how you might want to reword that statement, because your statement says that you can do this without compromising the integrity of your system. But as a tribologist, to me, you have significantly compromised the integrity of your system.
Oh, in fact, thank you for this comment. I missed. I think that I missed the problems related to this when I considered the reduction of the tightening torque. It was related to, in fact, to keep the structural stiffness. Maybe I write this in a wrong way, of course. But the idea here was to use the main factors from the Orion beam, that is to try to keep the resonance frequency close to the value of when the system behaves linearly. This was the idea. But yes, you're right. I think that we have saw in some results from here that even with these values of torque, we start to see some black traces on our pegs due to the frictional due to the friction that it is actuating in our contact pegs. Yes, I think that I should consider this and maybe rewrite the conclusions related to this phrase.
Yeah, it's a fine distinction, but I think that if you stick with stiffness, then that helps address it. I'm curious if you've looked at some of the long-term effects, like now that you're seeing that you've got the corrosive wear in your interface, that black speckle is oxides, aluminum oxide, from having heated it up and had fretting occur there. Have you seen that going back and retesting the system, have you seen that from the very start of your experimental campaign to the end that the linear frequency changed at all?
In fact, yes. After this, I'm not sure, but I have tested different beams and I have performed a lot of tests. And in the results that I have measured, I didn't see any changes with regard to the resonance frequencies. Yes, I have a variation due to each time that I assemble, I can see the variation in the results, but the variation on frequencies are not significant. So we will see the 6 bending mode around this frequency interval here. But this will be, of course, a question for future works. I intend to work more on this benchmark, of course, to then investigate the micro-scale effects after the experimental runs. This is, in fact, a good idea as next step.
Yeah, that's something that we've tried to adopt as our own internal best practices, measuring the linear frequency of the system before an experimental campaign and afterwards to see how much damage our system incurred due to it, especially when you're doing shaker excitation, because shaker excitation does lead to fretting, and fretting can occur in a matter of just a couple hours of excitation. So let's go back to that variability plot that you had. I think I don't have too many more questions. The rest I'll give to you by emailed comments. But the one where you showed the variability across disassemblies. That's
here. Okay.
Yeah. So for subplot A, how did you do anything to control for the alignment of your structure, or did you just kind of hand align it?
In fact, we have an assembly protocol that we have followed to keep always to try to be close to the same structural condition, because if we see that after assembly and disassembly we will have new structural conditions, but in this case we have tried to keep the repeatability of our measurements by using a protocol in which I have explained it a little bit more on the thesis, but we have followed always an assembly protocol, starting with the central bolt to ensure the alignment of the rows, and then after that the central bolt we have then put the external bolts on the structure.
Yeah, so the reason why I'm asking about this is that, say these are the two sides of your interface, and if you're just doing it by bolting it together, there's enough slot in the bolts that, instead of it being perfectly aligned, I'll just exaggerate, you'll get something that looks like this one time and like this another time. So you have some angular misalignment between the two interfaces, and that is my hypothesis, what's giving all that variation in subplot A. A nice idea that Sandia came up with, Rob Keither's group, was let's 3D print a little guide for assembling. Because, what we did in my group, we always just assembled it between two beams that were, we assumed they were straight and flat, and that worked pretty well. But Rob Keither's group had this really nice idea of 3D printing a guide so that you put the guide down, you assemble it with the guide on there, then you take the guide off so that you're guaranteed to minimize that alignment mismatch.
Wow, this is a very nice idea. Yes, I agree on this. There is an paper with regard to this. I would like to see, if possible, after.
I think you cited the paper. If you look at the papers where the C4 beam is developed by Rob Keither's group, then it's from one of the nomads, like maybe Nomad. Maybe it was IMAC 2019 or 2020 paper, but one of the Rob Keither papers, we'll talk about that. They had a little 3D printed alignment guide. And if you can't find details, then you're welcome to get in touch with me. My students are doing something similar for a different structure that Gael actually helped me design, or I designed with Gael, I should say.
Nice.
So Gael and I need to talk about that more in a little bit. Okay, very last question. I've asked you a lot. For the GP NARCS model, I have the same type of questions as I did for your identification method in chapter 4 about how you're handling nonlinearities, because it seems like the GP NARCS model, you are training it on one amplitude level. And when you think about applying this to structural health monitoring, like, I'm thinking about a bridge, like, or like some other application that, the amplitude level or excitation level is not going to be constant, but it's going to vary quite dramatically throughout the use. So with that thought in mind about what real jointed systems look like, you did a fantastic job with chapter 2. And in chapter 2, you realize that, you've got these amplitude dependent nonlinearities. So the stiffness is going to be highly amplitude dependent. The damping is going to be highly amplitude dependent. As you look forward to your future work, how do you plan on accounting for this amplitude dependency that you have that's not really reflected here with the specific form of the Bach-Winn model you're working with?
Yes, so in fact here, to increase the predictive capability of our model, yes, we have considered two amplitudes, two excitation amplitudes. In this case, in fact, this was a benchmark, the Bach-Winn was a benchmark, a challenging benchmark with a greater degree of difficulty to approximate the nonlinearity of the model. And the idea of using this value of excitation force here, the highest one, was to include the nonlinearities on our GP NARCS model. In fact, yes, here in this structure, the hysteresis loop is not so. The displacements in this dynamic system is not so. The nonlinear behavior is not so pronounced than in the Bach-Winn case, for instance. But with this numerical assessment, we think that the GP NARCS could reproduce well, even in a very nonlinear case, due to the framework of the NARCS model. We have saw in some works in literature that the NARCS model can reproduce well nonlinearities, very complex nonlinearities. But we still have problems with hysteresis due to the dependency, you're right, with our stiffness, with our nonlinear stiffness. But here in this case, in the GP NARCS, we have saw that it is possible to predict. For instance, it was not possible to predict the response of the Bach-Winn model by using, for instance, the simple NARCS model. But with the GP NARCS, we could reproduce the response of the system here. I think that the GP NARCS could be a very interesting tool, in fact, because we can deal with more complex systems than by using, for instance, the Volterra series or even the harmonic balance method, in fact.
Okay, very nice. One last easy question for you to answer before I shut up and let the next person ask questions. Back to the experiment. So I think if you go to slide 32.
Here it is.
Yeah. How did you clamp your experiments? Because both this and your other experiment, you had a clamp boundary condition. How did you reproduce a clamp boundary condition?
So here, in this case, so at the beginning, I had some problems with the alignment of this structure here. So I have performed some measurements with the distance from this side of the beam with relation to our table to keep the alignment of this structure. Then I have used some supports to keep the alignment of our structure, and then I have applied the tightening torque on these bolts here to ensure the clamping. In this case, unfortunately, I have not measured the velocity at this close to the clamped end. In the R on beam we have measured, we can state that in fact in that case we have a clamped end, but in this case we have not measured the velocity around this connection here. Thus, yes, I'm not sure if I can say that in this case we have a clamped condition. Maybe not exactly a clamped condition.
Yeah, so historically we've struggled with getting truly clamped boundary conditions, which is why we never do them in my group. You might be interested. Christoph Schwingschackel has a really good IMAG paper from maybe like 2014 or so, where he's looking at different ways to create a clamp boundary condition and the influence of different experimental setups on creating a clamp boundary condition. And if you can't find the paper, send me an email. I'll give it to you.
Okay,
because I've got it in my saved library. But just for future edification. Anyways, thank you for putting up with all my questions. As I said, I think you did a great job, and a lot of my comments are somewhat nitpicky, but a couple more in-depth ones that you did a great job answering. So I will turn the floor over to whoever is next. Thank you, Rafael.
Thank you very much, Professor. Thank you.
Okay, thank you very much, Professor Break. Your comments are welcome. I am sure that in the final version, Teloli will consider your suggestions to be tested. Now, I would like to invite Professor Varoto. Your comments and suggestions to Rafael. We are open. So Varoto, welcome.
Oh, thank you very much again, Samuel and Rafael, for your kind invitation. It's a great honor for me to be participating in your final defense. I appreciated very much your work. It's in my opinion, it's a very high standard PhD thesis, and most of the questions that I have, I will also forward to you on my PDF, as I told you before you start your presentation. But there are very minor suggestions regarding your text, nothing technical. And I just have a couple of questions to put it to you today, and I'll go directly to the experimental analysis on chapter 4, and particularly on figure 39. We could go back again to that figure.
I'll just share my screen.
Yeah, I was addressed previously on Professor's break questions, but I'd like to go back to that a little bit more. Yeah, I'm going to be waiting until you. Yes, right there. If I understand, right after the figure on your text, you say that figure 40A illustrates the receptance calculated. So it's a calculated receptance. If I understand correctly, your experimental apparatus on figure 39, you're not using a force transducer to measure the shaker force applied to the beam, correct?
Yes, correct.
Is there any particular reason why you're not using a force transducer on this experiment for measuring the applied force from the shaker?
Yes, so in fact, we have measured the load force, but however, we saw that, especially considering subsine tests and also stepped sine tests, we saw that the signal applied was not constant. The signal applied was not constant in the load cell. Due to this reason, we have considered instead the value of the voltage supplied on our shaker amplifier, and then we have identified a constant to transform the voltage into a force value.
Oh, okay, that also answers my following question. That since you are not measuring the force, but on figure 40, you're showing the receptance in meters per Newton. I just would like to ask, what did you use for your force reference? You're using the voltage signal from your signal generator, right?
Yes, the voltage signal times the constant to transform the voltage into a force value.
Okay, so when you say that you ran some previous tests with the force transducer, but the force is not constant along the frequency axis, what have you observed? Have you observed some drop off because of some resonances or some not negligible shaker structure interaction in your test? What have you observed in more details?
In fact, it was the first drop-off phenomenon.
The first drop off. Okay.
Yes.
So even putting your shaker on a place that is closer to your boundary condition, what in essence for testing like cantilever beams, as long as they're not too flexible, wouldn't be the best suitable position for the shaker. You have observed some drop off phenomenon, right?
Yes.
Okay. Okay. Yeah. Shaker testing has those little features that sometimes. It's not very useful, but okay, I understand your answer, and I'm pretty much
this was
satisfied.
the reason why we have considered the feedback controller in the application involving the Orion beam. It was especially to minimize the effects related to the first drop-off, since we were testing the step signs.
Okay. Yeah, another comment that I will forward to you on my PDF goes on the same line as Professor Brake was mentioning. I'd like to see some more details on your experimental description of your testing, because with it is written in sufficient details, but it's not completely described in such a way that I could reproduce your experiment in my lab. So when you describe an experiment, your description should be able to provide a reproducible testing conditions in other places. You understand what I mean? So, for example, have you employed in your tests, generally speaking, have you employed like window functions, like Henning functions, or did you use those?
To compute. In fact, here to compute the FRFs, I have considered here. In fact, when we have the white noise signal, yes, I have used it. In this signal, no, I have not used it because here we are dealing with sweep sign tests. I have considered the entire signal. But yes, I agree that I should include more details, further details with regard to this.
Okay. Specifically on the boundary conditions, because if you look at your testing, let's use again figure 39, but you can keep that slide that regarding the assemble and deassemble. Yeah, because I have a further question on that.
Okay.
But if we go back to your figure 39, actually on your beam, you have actually 3 boundary conditions that you could consider. You have your connections on your joint with the 2 or 3 bolts, dependent on which structure you're using. You have the connection with your shaker that could also be understood as a boundary condition, and you have the clamping. In the process of assembling and deassembling, did you also deassembled one of the beams from the clamping conditions, from the cantilever clamping, or you just left it there?
No, just the upper beam, the beam on the top. Yes, I have not disassembled the beam in the clamped condition.
Okay. Did you have a chance to look at some possible uncertainties coming from your major boundary condition, your clamping conditions?
In these experimental measurements, no, I haven't checked, in fact, but this is a very good point to explore.
Okay, because some part of your text, you mentioned that with a large clamping condition or a large clamping block associated with some bonding or some gluing your structure, and you also refer to our colleagues from Rio de Janeiro, Professor Sampaio and Professor Tiago Rito, that should help you to avoid the major influences from your cantilevered simulated boundary condition. Do you think that would be enough, or would you consider in the future to analyze a little bit more closely your boundary conditions, how they vary along the time, how the boat's torque vary, or generally speaking, to apply the same type of analysis that you applied on your joint, applying for the boundary condition? Have you considered that?
Yes, in fact, to avoid any kind of problems, here we have measured with a 3D vibrometer the velocity close to the clamped end to be sure that the displacements around the clamped end are close to zero. So in this condition, in this clamped end, we could see that in fact the displacement is close to zero in this experimental application. But in fact, in the other experimental application that I have showed here, we didn't perform it. So we didn't perform it. So I think that this could be an interesting next point to analysis.
Okay, wonderful. Just two quick final questions for you. One is a question, the other one is really a suggestion. If we go back again to use figure 39, I'm looking at your A part of the figure in your experimental setup, and I can see that on part A and part B that your joint is pretty much symmetrical with respect to the longitudinal axis of the beams. This is more like would sound like a silly question, but it's more like a curiosity for me. What would happen if you invert the positions of one of the boats? On figure A, on part A, you have like from bottom to up, you have like a boat, washer, nut. What would happen if on the right you would have the opposite, in the opposite alternate boat connections? Would you expect to see some different results?
No, in fact, because of course, to my opinion, the main properties related to the slip are here in the surface in contact. So due to this reason, yes, I should investigate this further, but at a first comment, I think that this won't influentiate the distribution here in our surface due to the symmetry in our structure.
Yeah, I encourage you to look at that issue in the future. If you would allow me to just to share my screen for 2 minutes, because I will show you the reason of my questions very quickly. The reason of my question is because we've been participating on a round robin experiment with at IMAC. Previous IMAC conferences, and this is what we call the BARC assembly. It's a round robin for trying to identify the modal characteristics of this type of a box assembly. Okay, and the guys from Sandia specifically have been in contact with Thailand Schorner here, and they really here, as you can see, they are suggesting that the bolted attachments would be done in alternating directions, as you can see here. See?
Okay.
So that would, when I read your work, I immediately started thinking about that experiment we've been working with, and with the guys from Sandia and several other universities, and some previous preliminary results have shown that when you invert the boat position, you have some differences in results. So I don't know if that's because of possible torque variations, I don't know, or some tribal or some friction, or I don't know, but that also attracted my attention when I was reading your work, and to ask you that question.
Well, this is maybe Professor Matthew Brake has some comment on it.
Yeah. Well, this is just. Go ahead, Professor Brake. You can comment on that.
I mean, I don't want to comment too much because this is Rafael's defense, not me answering questions. But we're also working on that system.
Yeah.
I know that a lot of the people that investigate that system glue the bolts in place.
Yes.
So it's rather maddening to look at most of the results you see there. But from looking at larger systems, the bolts are inert. They don't do much of anything. So okay. I suspect with the bark, because it's such a small system, the bolts have more influence. But
that's true.
Yeah, it's a great set of interesting questions, Paul. I really appreciate hearing your discussion about it.
Okay. Yeah, I agree with you, and it's a very interesting project.
Yes.
Yeah. Just one final remark, Rafael, before once again congratulating you on your great work, and also Samuel. I just would like to suggest, if you go back to your abstracts and your either in English and in Portuguese, try to make it a little bit smaller. Okay, try to fit it in a single page. Try to give your message for your reader in a very direct manner. It's extremely well written. I agree with everything you've done there, but abstracts are places on thesis where you have to give your message right away, and single page abstracts are ideal in terms of describing, even though your thesis is long, you've done a lot of excellent work, but that's the only suggestion as far as format is concerned. That is the only suggestion that I'd like to leave it here to you, and you will see it written on my PDF later on. But I just would like to tell you that right now. Okay.
Thank you for your suggestion.
Wonderful. Okay. Well, I'm very satisfied with your work. I wish you all the best in your future endeavors and your future challenges. We heard that you're going to spend some time in France. All the luck for you, all the best luck for you. And Samuel, once again, thank you enormously for giving me the opportunity to share some of your excellent work. And that will also impact our partnership and our collaboration. And thank you again and congratulations, Samuel, on this excellent supervision. Rafael, congratulations once again. Thank you very much.
It was a pleasure. Thank you.
Thank you.
Okay, Professor Varoto, thank you very much for your comments. And now I would like to invite Professor Daniel Castello for consideration, and thank again to accept to participate in this jury. Thank you.
Oh, thank you, Samuel, for the invitation. Thank you very much. Thank you, Gael, for the invitation, Rafael. That is a great pleasure for me to be here, being part of the jury. Rafael, you have done a tremendous work.
Thank you, Professor.
Yeah, that is very interesting. I would like to say that your presentation was very organized and very clear. Your manuscript is of high quality. The figures, the discussions, the literature review, the results, and so it was really interesting to read. I read some parts of it because you have a tremendous amount of work, so I started reading, but I couldn't read everything. But in this point, it is very good for you, and you have already made some contributions in the literature, and I'm quite happy for you. You have published papers in very good journals. And I also see that you and Professor Samuel and Professor Gael, you have some new papers to be released under review. So congratulations for your work. And as Professor Varoto said, that is very good that you have the opportunity to continue some time abroad your work. I have some small questions. I would like to come back to the same figure that
yes, of course.
Yeah, because there is something really interesting in that figure. When you show that when you disassemble the system, you have different profiles. I have several questions for these because there is one important thing that when we work with inference, and you have the experimental setup. Of course, that if you keep the same assembly, the amount of uncertainty in experimental data will be this one. But every time that you disassemble and you assemble the system, you have a large amount of variance in data. That is perfectly normal, and that is represented in your figure A. Okay, but in your case, when you say you disassemble the clamp and the tighteners, or you disassemble only the tighteners, the screws?
What is here? Yes. When we consider the disassembly, we consider the complete disassembly of the superior beam in our lap joint configuration. So
but you mean the clamp and the screws, or no?
No, the clamp is always clamped.
Okay, yes, because that is really important. I remember that once we made some experiment, but it was with a different goal, but working with composite beams, and we have done lots of measurements for modal analysis, and we had some level of discrepancy. But when we disassembled the clamps and we clamped again, everything changed a lot. But we didn't change the clamp. The only thing that we did was to disassemble and assemble it again. Why I am asking you this? Because, for example, if we have some goal of damage identification or diagnostics, this type of information that is present in A, it will be quite important. Yes. And my question is, when you show this figure in A, did you took this into account when you performed your inference, or you decided to take data from one single assembly and started making all your calibration and validation?
So here in this work, regarding the application of the RMB, we have considered one single measurement. After that, we assemble it, because we have saw that yes, when we not perform the disassembly, the repeatability of the structure is pretty high, and from that we have considered these tests performed without disassembly the beam. They have been performed in a single experimental run. We have just changed the tightening torque applied.
Okay, why I'm telling you this, because probably what we will obtain in this case, if we consider calibration using data from specific assembly number 1, specific assembly number 2, and a specific assembly number 3, possibly we will have cluster of parameter values in the parameter space. That is the possibility that we will have. I'm telling you this because in practice you have to face all these scatter, and you probably do not know which slot you will be. I mean, in which cluster you will be. So perhaps I don't know. That's one suggestion, that perhaps you could try to take this, not for this is perfect, but for extending work, to try to take these clusters into account.
Yes, thank you for your suggestion, Professor. We have started our work considering this. We have considered different assemblies and disassemblies exactly to infer the difference on the tightening torque applied on the bolts. We have saw that, in fact, after assembly and disassembly, we have a new, I could say, we have a new structural condition. Specifically speaking, when we are considering the different values of torque, the clusters related to the linear case and to the nonlinear case, it starts to be assembled. And this is very difficult to identify where we are considering a linear case and where we have the loss of the tightening torque. And I think that this is a very good point, and we started to investigate it, but we will see this further in the next works. This is a very good point.
Yeah, because that's I'm glad to hear that you are keeping your work on this topic, because it is quite interesting. And as you mentioned that you are going to talk with SHM, Structural Health Monitoring, and we know that in some situations the variations that in dynamic data, modal data, is quite small, and in that case, that previous figure, perhaps that variation is inside the envelope of the damage, the changes due to the damage. So it could mask the damage.
Yes.
So that is a very, very interesting point for you to investigate.
Not even in this assembly, but also when you consider different excitation conditions, we can see that here we have a mystery between all of these figures. This is also a challenging issue.
A challenging issue, yes. But the important point here is that when you present all of these, and it becomes quite clear for us the importance of try to treat all of these simultaneously. So that is incredible how we can see in this experimental setup that you have created and proposed. So it is very clear in these points. Okay, let me ask you something about another point. When you use, for example, the GP NARCs, okay, so what we are trying to do? We are trying to build some equivalent model to describe that phenomenon.
Yes.
Excellent idea. Okay, so we get data, and we choose some kind of model structure that we believe that can, in certain way, describe that dynamic behavior. And after this, in your case, what I got is that as this equivalent model not necessarily has something related to physics, you have lots of parameters, and so in some sense you need to use some kind of model selection, not to use some model with thousands of parameters, but I understood that you ran lots of times the optimization, the training, and after this you decided for, I would say, the most parsimonious model. That's what you did.
Yes.
Okay.
In fact, we have tried.
Sorry?
We have tried to balance the value of fit and also the number of regressors used in both output and input legs to minimize, of course, in fact, the GPNARCs minimizes the problem of overparameterization. Because here we are not dealing with the parameters with regard to the NARCs framework. We are dealing only with the legs.
But the legs, I haven't never worked with this, but the legs is related to the number of parameters. No, because when you mention the legs, I mean you are going to take lots of the time history. I mean the input and output. The point is that you have legs in the output and legs in the input, but you do not know how many legs you are going to consider for both of them.
Yes. At the beginning, no. We don't have this structure. It's the optimization. It's something like trial and error.
Okay, but how did you choose the most parsimonious model? By the fitting output this. How did you choose that red point?
Here, in fact, we have considered different value. We have considered all of these combinations in the output legs and also in the input legs. We have then updated our model. We have performed the optimization of the parameters and then computed the value of fit. Based on that, we have constructed the surface and we have selected this red dot based on the minor quantity of legs in our output and also in our input that provide the highest value of fit.
Okay.
This was the idea.
Okay, no, but that's one strategy. Okay.
Yes,
Because
yes, in fact.
when we use Archaic, for example, Archaic generates lots of solutions, and from all the solutions, there is a specific strategy that you can take the most parsimonious one. Okay, that's one point. And there is something that I'd like to ask you, because in this case that you are using nonlinear, an equivalent model to describe nonlinear phenomena, my question is, can you, in certain sense, define a domain of applicability of these?
Okay, this is a good point. This was the idea behind using different time signals. The idea was because when we are dealing with black box model, generally we have problems that the conditions in which we can predict the response are close to the training data considered. So in this case, we tried to propose a model the more general as possible, based on the subsign test, and then we have validated considering different signals. We have considered then the per sign and also the white noise. We have not considered different excitation signals from this one, but we will probably have problems with regard to the nonlinearity. So if we increase the excitation amplitude, we will probably be far from the predictive capability of our model. So at this point, I could say that the limit that in which we can use this problem is related to the excitation input that we will consider, which is of course closely related to the nonlinearity present on your system. So if you increase the influence of the nonlinearity, probably that our model will lose its capability of prediction.
Okay, so that's important. Possibly you have written this, but or possibly I have missed this in the text, but it is important point, because as it is nonlinear, it would be interesting to define, at least to try to define some domain of applicability of this equivalent or surrogate model.
Yes.
Okay.
Yes, I agree. This is true. In fact, all of these problems that I have worked are based on the global analysis, considering isolated vibrating modes. So at the beginning, I could say that the limitation of the methodologies that I proposed here is to deal with isolated nonlinear modes. So this is the first limitation. Of course, that we can expand the applications from this work to multiple degrees of freedom systems. But at the beginning, I could say that our main limitation is related to this, and also to the degree of nonlinearity.
Okay. I have just one more question. When you performed your calibration using frequency data, how did you define the variance of the measured data that you use on your likelihood functions?
Okay, so in this case, I will start here.
This one?
Okay.
I mean, yeah, how did you define this sigma, which is the variance of the experimental data?
I have considered the variance on the entire response. I have computed the variance with regard to these different experimental measurements, and from that I have proposed the initial value for the covariance to be used on our likelihood function.
Okay, that's perfect. So I mean, you have, I don't know how many measurements you got for the frequency response function, but after a collection, 5?
5, yes. In this case, it was 5.
Okay, so you can sweep each frequency, and you can obtain the mean value and a variance, and from this set of variances, you can choose some reasonable variable for the variance of the experimental data. So yes, that's perfect. That's okay for me. Okay, so Rafael, I don't think I have many more to tell you. I have only one more question. Could you put in your slide 29, please?
Yes, of course.
That is only a curiosity.
Uh-huh.
29.
Here it is. Oh, sorry. I have a lot of slides. 29.
Yes, this one. I have only one question, maybe two questions, but when you write choices for covariance function, mater, 3/2, okay. When you choose that covariance seems to be something like this one, or no? Something
Sorry.
like it is two picked, or no?
I'm not sure. Wait.
No, just is a curiosity, because it is the. Oh, sorry. So let me turn it off. It is a curiosity because, for example, when you use matter, you are telling me that you have a parameter to measure the magnitude of the variance, which is sigma m squared, and you have the product of two functions. Okay. The function that is the exponential, it is maximum, it is when x and x prime are equal. Okay, but when you take a look at the other function, which has this 1 plus 3 squared root, okay, the minimum value is at when x is equal to x prime. Is it okay?
To be honest, in this case, the covariance, they were already implemented on the software that we have used to identify the model. Of course, that we could select many different kinds of covariance functions. The selection in this case was performed based on the covariance functions that promoted the best results. This was the idea. To answer at this point, I think that I don't have the best ways to explain the relations here, but of course I'll investigate it further.
Okay, well, that's a curiosity because in this case, I'm going to show you a figure.
Okay, I will see.
But it is only a curiosity. The second one is this. That is the exponential when x is equal to x prime. Is it okay?
Okay.
And the other one is something like, I don't know, something like this. Is it okay? Because the other one, there is an absolute value. Oh, so it was a curiosity. Why did we choose these? Okay, but if you're telling me that in this case you have a package and you could choose lots of options, I understand that we can choose some of them such that we can perform the calibration. After this, we can perform some kind of analysis to define which one is the most suitable one for our application cases.
Yes, this was the case. Yes, this was the
because it's a surrogate. Yeah, because it's a surrogate model. I mean, in this case, it could be the best one for you, but perhaps in 2 months you are going to work with some other problem, and this one is not as good as for this application, but you've got to choose another one.
Yes, this is exactly the problem.
Okay. I don't know if it is written in the manuscript, but perhaps you I don't know if you have tried some different forms of these, shapes of these, but if you have tried, you could write one line, and then you can write simply that this one was the most feasible one for this kind of application that you have.
Oh yes, in fact, we have written a line that explains exactly this, that this was the selection to this work, to the application that we have explored.
Okay, so I'm going to finish. Rafael, thank you very much for the invitation. Gael, thank you very much. Samuel, thank you very much. Congratulations for your work. congratulations for the advisors. And I finish my comments and I pass the word to Professor Samuel.
Thank you, Professor.
Thank you again for
Thank you
your
very
comments,
much.
your suggestion, Professor Castello. And the last question is really interesting, and you can help us because I have one PhD student that we start to develop more this part of GPN arcs to apply this for SHM applying in vaulted joints. I think this stuff comments is really important, really interesting to back explain what we can choose a best way to decide the kernel functions in GPN arcs. I think it is welcome comments. Thank you very much.
Welcome.
Now I would like to invite Professor João Antônio to the considerations and comments. Thank you to accept the invitation. Thank you.
Okay, Samuel, thank you for invitation. First of all, I would like to thanks for the invitation to Samuel and also Rafael. I will say that's a pleasure to take part of this work that you have been done. And I would like to congratulate you and Samuel and also Professor Gael for the excellent work. For me, Rafael, it's a pleasure to take part of this work. And I was just to say that I was taking attention in your presentation and came back to 10 years ago, something like that, when I took part not in one jury, but when you presented an undergraduate work, and you say, "Oh, professor, I did understand your question," and so on, and I feel very, very grateful to see how you improved and your level today from that time. For me, it's a very pleasure to see you're growing in a scientific way. It's really congratulations.
You are part, Professor, of all of this. You are part of this work, and I thank you for your collaboration until now.
Okay, it's a really very nice thing to see. Like when sun growing. Most of the thing I think already the colleagues already answer main points. It's already discussed. I have just a small thing that I would like to. It's more curious. I would like to say that your work, it's the test. It's very good. You presented the initial, the middle, and the end of the work. It's the theory. It's already posted in the text. You presented some simulate and also some experimental parts. I can say that for me it's a complete work. I posted something here. Okay, it's most of them. It's already discussed. It's something that I had to ask to you, but Professor Paulo Varotto already did. But put the slide 18.
Here it is. 18. Here.
Yes. The other it's the same slide, but the other figure is
Okay.
okay. The below.
Oh, okay.
Okay. It's more curiosity because I saw your beam. It's a slight beam, and I was thinking about the assembly, and I would like to ask you if you just put two bolts like this for a continuous beam.
Okay.
And
Without the connection.
without the connection.
Okay.
And excite this structure because it's not a robust structure. Could you identify some non-linearity of the system? Because the level of the force is large. I suppose that you find some non-linearity on this system. Did you make some tests in this way?
No, in fact, in the bolt joints community, it is very common to test the beams in the monolithic condition. The results that I have shown in the Orion beam, we have considered the monolithic conditions to estimate the frequency response functions. But in this case, we have not considered this. This was the first experimental application that we have investigated. In this case, specifically speaking, I don't know if we will see the nonlinearities, because if so, the response, I guess it is supposed to be combined with the nonlinearity from the softening effect. So if we have a look on the frequency response curves, we have the main factors that is present from the nonlinearity when we have the presence of joints. Thus, due to this reason, I think that in this case, in the monolithic condition, I think that the behavior is close to the linear with the excitation force that we have considered. Maybe, of course, we could see some interactions from the beam and also the clamp, which we should investigate in more detail. But in this case, I really don't know if because okay, we could see some nonlinearities related to the geometry due to the due to the amplitudes at the tip of the beam, for instance. So at the highest levels of amplitudes, we could see the start of the nonlinear behavior. But specifically speaking, in this case, I think that the behavior of the beam, it was supposed to be linear, close to the linear.
Okay, because I was a little bit curious because to see it in a continuous beam, to see the effect, also the size of the bolts. It's a little. I think it has some influence, like concentrated mass for this kind of beam.
Because, for instance, if you consider even the Orion beam, and this could be interesting for the discussion, if we see the nonlinear behavior of the Orion beam, even in the glue condition, when we have the contact packs glued, we can see that here we have the presence of nonlinearities. However, when we compare the nonlinear behavior present in these curves with relation to the nonlinear behavior of the other curves, and also considering the frequency interval that we are dealing here, it is supposed that at this location we could predict the behavior of this condition by using, for instance, a linear condition, a linear model. Of course, that here we have chains, but they are not pronounced. The chains here are just slightly. So in this case, probably a linear model could fit well the behavior of our structure. Of course, that probably we will see similar behavior on that structure, but the nonlinearity comes from the presence of the joint.
Okay, thank you. Another thing that just more curious, because I suppose that your work, it's good work, and someone will try to reproduce and to use this work to reproduce or also to apply it. And how did you define the initial parameters of the book when you just put one table there and I didn't see, I don't know if I lose some comments that you did, how to do started with that parameter.
Okay, so at the beginning, to update these parameters, we must select a prior distribution. The interval that we have selected to the prior distribution was performed based on sequential programming optimization that we have performed on the book one. We have some conditions that we must consider. We have some conditions, maybe here in the text I could explain it better. But we have some interval of parameters that we have proposed. Let me just find this in my... Here it is. Here it is. So to define, I have performed this. I have minimized this function based on the sequential quadratic program. And we have these conditions here, in which we must consider that the parameter alpha must be inferior than our resonance frequency. So we have some conditions based on the physical behavior of our structure. And after analyzing the behavior, for instance, we also know that the softening behavior is present on the system response. Thus, we also have conditions to be sure that the book one model will also reproduce the softening effect on our system. This was based on changing. This was based on some conditions to our first problem, to problem in which we have defined the prior distribution. So we have performed at first on a physical. We have performed first physical insight on the system response. We know some of the ingredients that we must consider when we are dealing with bottom joints. For instance, again, the softening stiffness and also the hysteresis loop, the shape of the hysteresis loop. And based on that, we have proposed the interval for the book one parameters.
Okay. Just on find comments, and I would like to hear from you. Do you think that you can use this same approach for not a laboratory structure, for a real structure? What do you say about?
So at first, with regard to the Volterra surface representation, we have more limitations on it. The first one is that we must consider that the hysteresis loop is almost closed. In this case, we have dealt with a condition in which it was easy to confirm that this condition was satisfied. For instance, a multi-degrees of freedom to an experimental to industrial scale case. At the beginning, I think that we will have some limitations, maybe to propose a different way to update the Volterra kernels. For instance, approximating by considering, instead of the frequency response functions, using the time representation of these functions to perform an analysis directly on the time domain response to update these parameters. But at the beginning, yes, I think that we have some limitations, especially because we must satisfy this condition, the behavior of our system lies in the weakly hysteretic.
Okay, my question is because most of the real structure, the condition of weakly damping and weakly is not verified. Because that. Anyway, it's okay for me. I would just say congratulations for you, for the advisor Samuel and Professor Gael. And thank you for the invitation. That's all.
Okay, thank you, João Antônio, for questions.
Thank you.
Now, I would like to invite Professor Gael Chevalier, who was the co-advisor of Rafael, and he has a large contribution to conclude this work. Welcome, Gael.
Hi, do you hear me?
Yes.
Yeah.
Okay. I'm sorry, I'm not sure the camera is working. Can you see me now? Okay.
Yes.
Thank you, Samuel. First, I would like to thank Samuel because he invited me to participate to this supervision, and it was really a great pleasure to work with you, Samuel. And of course, in a second time, I want to thank you, Rafael, because working with you was really a great experience. I think we learned a lot together working
Yes.
in France last year. I will be back about this topic. I would like also to thank the Defense Committee, so Paulo, Matthew, Daniel, Joao, for accepting to participate to this committee. It was really interesting to hear and to listen to your questions and suggestions, and many things will help us, I think, to improve the work we did with Rafael. Just one technical point is there were a lot of questions about the repeatability of the results you obtained, Rafael, on the Orion benchmark. I think something you have to keep in mind analyzing these results is this benchmark has been designed with thin structures, thin plates. And it is a very, very different point from other benchmarks. Here, it's much easy to reproduce the force, the tightening force. And especially, I want to come back to the question Matthews asked. It was the question about the repeatability of the tightening torque. Of course, you're right, Matthew. It's very difficult to reproduce this tightening torque for most of the structure. In this case, we, of course, took care about this point, and the use of thin plate helped a lot for repeatability. So that's all for technical things. I want to be back on Rafael works. It was a very nice experience to welcome you in France last year, but it was also the year of the COVID. So
Yes.
Everyone have to keep in mind that Rafael has had 6 months free to come to the lab, to work with me and so on. And I don't know, maybe 3 months, that's the number, at home in a small flat in France, close but also far from the lab. The meetings were using Zoom and Teams and Google Meet and so on. We learned a lot about these tools, but it was less efficient, as you can imagine. But of course, we also did a lot. We worked a lot. We published a lot, thanks to you, Samuel and Rafael. I hope we will continue to work. It's very interesting to work in research with Brazilian colleagues. I would like to say something about Brazil, especially for research. To me, it's very complementary from what we are doing in France. You are really the specialists of data processing, signal processing, very good researchers in structural dynamics too. I think we have maybe much more experimental devices here in France. So it's very interesting to work with you. And I think, and I hope we'll continue this work together. I got only one question for you, Rafael. Now, if you go to the slide number 50, does not exist. So
Okay.
not necessary to look at this slide. No, it's a joke for the number of the slide, but I really have one question. If you have the opportunity to work again about jointed structure, and I'm sure you will have the opportunity, what would be for you, if you are going far from what you did during the thesis, what would be your own topic? I think the topic of Samuel is now SHM and the methods he develops around your thesis, but also around other theses. I am much more a specialist about these benchmarks and about modeling these benchmarks, but what would be your own specialty on jointed structure in the future?
I think that I can work very well with the modeling of these structures. I like to understand the physical constraints, the physical behavior of these structures, and also understand why we have such kind features. For instance, why we have the softening behavior, why we have the nonlinear damping, and the questions behind the contact. So this was this. I think that now this is my quality. I can work on modeling it. This was one of the main ingredients, for instance, to propose the Gaussian process NARCs. Of course, that we are dealing with a machine learning model, but it was necessary to understand the physical behavior behind the jointed structures. So I think that now, from now on, I am able to work with model properties of this kind of structure.
Yeah, I agree. I think in the future, the challenge, but it's for the next generation, for your generation, will be to work both with physical-based model. We are able, our generation, Samuel and myself, to work with physical-based model. I think your generation will have to merge data-based models and physical-based models. So I think it's a pretty good idea to go in this direction. Yes. Thank you, Rafael, again. And I hope to see you soon. And also, I hope to see every members of this committee in real life, not in a remote way, soon. So, see you.
Thank you, Gael.
Okay, thank you, Gael. I think it's more interesting that to have to do the research and to get the result. I think it's the meet friends, okay, meet friends. And so that thing, I think when we have working, we collaborate with friends, I think the results will be better to us. And I expect in the near future, when the pandemic is over, we have to spend some weeks in Ilha Solteira, some years in the future. So finally, I would like to thank again for the comments and discussion. I'm sure that the final version of the thesis of the Teloli includes all these comments to improve the test. So my comments were not in the technical way, because during these years we asked and discussed a lot with Teloli about the technical results. So I would like only to say that Teloli developed this work during almost the last 7 years, including the scientific initiation when he was undergraduate course, working the same topic in the same area. It's interesting to hear the comments about Professor João Antônio, because Professor João Antônio can meet Rafael 10 years ago, and you could see, you could observe this growing of research. And now Teloli is a research engineer to work and to contribute to this area, not only in the academy, but he has a lot of knowledge that you can improve the industrial application. And I guess in the near future, he can contribute more. So for me, it's a satisfaction, and I really satisfaction to be part of this. Teloli demonstrate a right capability, in my opinion, to make research in an independent way. It's important to say this, because several points of this thesis were motivated and proposed by him. Okay, we have an initial idea with some topics, and he is able to work with these points because he's a well-organized person with a methodic to describe the results and to reach a focus. Okay, and I expect him to could contribute more in this area in the future. Now I'm very happy because he will start an international career at Besançon, and I guess that Teloli can return soon to Brazil to apply this knowledge with us in the industrial field. Okay, so again, Teloli, congratulations on your work, and appreciate very much to share the knowledge with you and to work with you. And I hope to keep on working together in the future.
Yes, of course.
Okay, now I get out the streaming because we have to meet it with the committee to give the final results, and after we can start the streaming. And Teloli, I invite you to get out the room.
Okay.
And contact you on WhatsApp to return to the meeting.
Okay,
Give
of
the
course.
results. Thank you very much.
Thank you. Thank
See
you.
you soon.
Thank you again.
Okay.
Valeu, pessoal, por vocês que assistiram e acompanharam aí a transmissão. Eu vou encerrar aqui, vou aguardar o resultado final da apresentação, mas muito obrigado pela companhia de vocês e por terem participado dessa